Outer space holds a weapon 100 million times more powerful than an atomic bomb. One strike, and it could black out a continent. From the space age to the Stone Age, in a flash. The weapon isn't man-made. It's our sun.
It's always a question of when the next one will happen. It's not a question of will they suddenly go away.
We've been hit before. We're in its sights again. Quebec, March 13th, 1989. The city is in the grip of winter. Temperatures are below freezing. Suddenly at 2:44 a.m., a 100-ton transformer on the Montreal power grid overloads. Blackout. The city is plunged into darkness. 6 million people left powerless. Astronomer Sten Odenwald explains how the night unfolds.
All the lights went out, quite literally. It only took about 90 seconds for fully operational to complete blackout conditions.
At dawn, the thermometer reads just 8 degrees, and the power's still out. Life or death work runs on emergency generators. The blackout lasts 12 hours. But the disaster could have been much worse. If not for a few transformers in the US, millions of Americans might have lost power too.
With only a couple of more components damaged, the entire East Coast would probably have gone down as well.
But what caused the transformers to overload so violently? Why did Quebec plunge into darkness? This wasn't a terrorist attack or human error. The culprit wasn't of the Earth. It was the result of a gigantic explosion 93 million miles away on the sun. Three days before the power network collapses, astronomers at the Space Weather Prediction Center in Colorado monitor an active region on the sun, when suddenly a giant explosion bursts from its surface. A white flash thousands of miles across and millions of degrees hot. 93 million miles later, a huge wave of radiation slams into Earth's atmosphere. Colored lights dance across the night sky from Alaska to Mexico. Quebec is hit by an invisible but immense natural phenomenon. A solar storm. An explosion of the sun so awesome, and a wave of energy so huge, it's almost impossible to measure. Space weather scientist Joe Kunches is blown away by the scale of these storms.
Billions or trillions of tons of matter is thrown off the sun at 1 million or so miles per hour. And I think it bodes towards the difference between terrestrial weather scales, where you might have wind speeds in the extreme of hundreds of miles an hour in a very strong hurricane or a tornado, to looking out at the solar wind, and the solar wind typically is 1 million miles per hour.
The solar storm that hit Quebec is the worst in living memory. But worse may strike the Earth in the future. And next time, we might not be so lucky. The sun is capable of producing storms that could black out whole continents. North America would be crippled.
Losing the electric power grid, even temporarily over an entire continent, is a major disruption to the way we operate in the 21st century.
Our lives are more complex and technologically advanced than ever before. But the freedom technology brings us could also be our downfall. Anything relying on the power grid when a solar storm strikes is vulnerable. But what causes a solar storm? How do they wreak so much havoc here on Earth? And is there any way to protect ourselves from future attacks? Scientists need to unravel the mysteries surrounding the sun and reveal the anatomy of a solar storm. The investigation begins 93 million miles away. The Sun is a 900,000-mile-wide ball of gas, mainly hydrogen. It's so vast, you could fit over 1 million Earths inside it, with room to spare. All the Sun's energy is generated deep within its heart, at the core. Temperatures here reach 27 million degrees, thousands of times hotter than Earth's most extreme forest fires. Every second, millions of tons of hydrogen are converted into helium. This nuclear fusion produces over 5 million tons of energy. The Sun radiates more energy in 1 second than the world has used since time began. The byproduct of all this energy is vast amounts of magnetism. Huge magnetic fields loop across the surface. They bubble up from the core and punch hundreds of thousands of miles into the solar atmosphere before plunging back down again. These arcs are so vast, the Earth could fly through one, with 100,000 miles to spare on each side. On planets like the Earth, every part makes a full revolution around its axis each day. But the Sun is a dynamic ball of gas. Its equator rotates in 25 days, but the poles take 35 days. The magnetic loops stretch and distort as it turns. Along each loop flow billions of tons of superheated plasma, electrically charged protons and electrons. A single loop contains the energy equivalent to 10 million volcanoes erupting at once. These loops are sometimes the first sign of an impending solar storm. Professor Paul Bellin wants to find out how these loops lead to a solar storm. So he recreates the surface of the Sun in his lab.
We have the main ingredients of what goes on in the Sun. We set up a magnetic field that is arched. We have a plasma there that can conduct electricity just like the plasma on the Sun. And we drive an electric current along the arch just like on the Sun.
With all the ingredients of the Sun in place, Bellin passes an electric charge through the experiment. Bellin's work shows these arcs are unstable. They twist and stretch in all directions. When they collide, they short circuit, like crossed wires. All their energy is released in a spark, a white-hot flash. The same phenomenon we see on the Sun. A solar flare.
It's a little bit like seeing a hurricane develop. You can see the precursors of something that might blow up on the Sun. You have currents, magnetic fields, the currents make forces, and if they add up in the right way, you can get very powerful forces that can cause these structures to blow up.
Bellin's lab flares release only a small amount of energy. If the energy packed into a solar flare was unleashed on Earth, the explosion could level whole cities. The The shock waves would be felt on the other side of the Earth. Nearly all life would be wiped out. Far stronger than the world's nuclear arsenal.
The smallest of the flares are more than 1 million nuclear bombs going off. The largest ones are 1 million times 1 million of these bombs going off.
Dr. Carol Shriver studies the power of solar flares.
A large flare is a vast amount of energy. It has no counterpart on Earth.
One solar flare packs enough energy to power America for thousands of years. In 1997, NASA captures this image of the sun's surface the moment after a solar flare explodes. It shows a shock wave, a ripple, racing thousands of miles across the surface. It travels so fast, it could circle the Earth in less than a minute. A solar flare packs a huge punch, but it isn't responsible for Quebec's power failure. It is the first stage of a devastating onslaught. Like the flash from a gun, it's the bullet that follows which causes the damage. Behind nearly all solar flares is a gigantic cloud of radiation, and in its sights, Earth. But its first victims are in outer space. For years, space scientists have known of the threat posed by solar storms. But the sun is unpredictable, and sometimes even NASA can be taken by surprise. May 14th, 1973. America's first space station, Skylab, launches.
Moving up. Skylab has cleared the tower.
Its mission, to prove that humans can live for long periods of time in space, and to expand our view of distant planets and stars. In total, 9 astronauts visit the station. The longest stay is 84 days. But Skylab is plagued with mechanical problems. And in 1974, it is abandoned by its crew and left to await repair. But in 1979, something knocks Skylab out of space. Scientists discover that between 1974 and 79, the sun fires a barrage of solar flares toward Skylab. But it isn't the flares that bring the spacecraft down. It's what follows. Minutes behind each flare is a gigantic wave of radiation. The wave contains huge amounts of electromagnetic energy, X-rays and gamma rays straight from the surface of the sun. The wave travels at the speed of light and smashes into the Earth's upper atmosphere, which heats and expands.
Solar storms, especially solar flares, dump enormous amounts of energy into the upper atmosphere. The upper atmosphere responds by heating up from 500 degrees to 1500 degrees, and that also causes it to expand out by up to 1,000 miles.
The swollen atmosphere envelops Skylab. The space station is suddenly surrounded by air, where once there was nothing but space. Air drag slows the satellite down, and it begins to fall out of orbit. In July 1979, Skylab crashes to Earth. Luckily, much of Skylab burned up on re-entry. Without regular boosts, thousands of satellites could suffer the same fate as Skylab. The multi-billion-dollar International Space Station is at risk.
Even the International Space Station has to worry about solar storms. It typically loses about 75 yards of altitude every day, and during solar storms, it can lose quite a bit more than that.
But the biggest threat from solar storms isn't to our technology. Radiation can kill. NASA's Neil Zapp is all too aware of the dangers faced by astronauts on all space missions.
Our major problem is that we don't have control over the situation. It's not as easy as turning something off or sending someone home or taking them out of an area. It's very difficult for us to get people out of harm's way once they're in orbit.
No one knows when the next solar storm will strike. And they travel so fast, early warning is next to impossible.
We confirm ignition and the thrusters go.
In 1972, NASA has a close call. In April, Apollo 16 lands on the moon. 8 months later, Apollo 17 touches down.
During the space between these two missions, between Apollo 16 and Apollo 17, there was this large event.
A storm breaks on the surface of the sun. 10 billion tons of radiation rains down on the moon. Unlike the Earth, the moon has no atmosphere to protect humans from the effects of radiation. If the astronauts had been here when the storm struck, they would have absorbed a potentially lethal dose of radiation.
It wasn't by planning. It wasn't intelligent planning that provided for putting the event in the dead space. It was actually a little bit of luck of the draw at that time.
But what happens when a massive solar storm is aimed straight at the Earth? We can't simply move out of the way. For all their power, these bursts of radiation are mere ripples spreading into interplanetary space. The solar storm that hit Quebec is a tsunami. March 13th, 1989. Across the Northern Hemisphere, millions witness a dazzling light show called the Aurora Borealis, the Northern Lights. These sparks are a visible sign of a clash hundreds of miles above the Earth's surface, a war between the sun and the Earth's invisible defense shield, the magnetosphere. Nicola Fox knows the shield like her own backyard.
The sun gives us everything that we need to be able to survive here on Earth, but equally it could take that all away in a split second if we didn't have the magnetosphere to protect us.
The magnetosphere completely envelops the entire planet. This invisible shield flows out from the Earth's core. It punches through the South Pole, cocoons the entire Earth, then plunges back down through the North Pole. Without the magnetosphere, all life on Earth would be vulnerable to high-energy solar radiation. These particles can penetrate living tissue and cause severe damage to cells. When the March 13th radiation cloud collides with the shield, most of the charged particles are deflected safely around the Earth and back out into space. But some radiation does leak in at the poles.
And that really churns up the whole magnetosphere, makes it go to very different configurations than it would normally be in. And in order to redress that balance, because nature always has to be balanced, the aurora are powered.
These mysterious displays of colored lights form when solar particles slam into gases in the atmosphere and cause them to glow. The more powerful the storm, the more dramatic the auroras. This high-altitude battle can cause problems for airliners. At the poles, the atmosphere is especially vulnerable to large bursts of radiation. The wave of energy causes havoc in the upper atmosphere, disrupting GPS systems and blacking out radio signals.
During intense storms, passenger aircraft have to divert to lower altitudes in order to regain communication with air traffic control.
On March 9th, 1989, as the radiation from the flare arrives at Earth's upper atmosphere, the battle with the magnetosphere begins. But in Quebec, the power stays on. 4 days later, on March 13th, a second wave of radiation hits the Earth's atmosphere. And the aurora puts on an awesome show. As the northern lights dance in the sky, the lights in Quebec suddenly go out. How does a radiation cloud high in the atmosphere shut down an electricity network on Earth? To find out, NASA develops the OSO-7 satellite. It can aim a battery of UV and X-ray telescopes at the sun. The mission will give scientists their first glimpse of a monster. This white spot might not look impressive, but it's the first image ever captured of the most powerful event in our solar system. It's called a coronal mass ejection, or CME. 10 billion tons of material explodes from the atmosphere of the sun, an enormous eruption. Without Earth's magnetosphere for protection, high-energy particles from the blast could begin to strip away our atmosphere. If a solar flare is the muzzle burst from a gun, then the CME is the bullet. Scientists still don't know exactly why CMEs occur. They're formed from the sun's corona, the atmosphere that surrounds the sun and stretches millions of miles out into space. Temperatures here reach nearly 3 million degrees Fahrenheit, almost 200 times hotter than the surface.
There are magnetic turbulence and magnetic forces lower down in the solar atmosphere that cause literally the outer atmosphere to be blown out into space.
CMEs are an electrified tangle of charged particles and magnetic fields, a superheated bullet of matter from the sun. A CME looks like a solar flare, but it's 100 times more powerful.
Before we knew of CMEs, we thought that the magnetic storms that occurred on Earth were a consequence of this brightening that was seen at the sun, the flare. And as we've learned more about the sun, we've realized that it's the CME that actually causes the magnetic storm.
Roughly half the time a solar flare occurs, a CME follows. But it travels hundreds of times slower.
It is a mass of coronal material that's coming off the sun, and that travels with the solar wind that streams continuously away from the sun at about 1 million miles an hour. So it takes about 93 hours for it to get to Earth.
On March 9th, a solar flare kicks up a wave of radiation from the sun. The wave travels at the speed of light across space. It hits the Earth's atmosphere in just 8 minutes. The coronal mass ejection arrives 4 days later. This is what causes the blackout. Unlike a solar flare, a CME isn't a spray of radiation. It's a barrage.
And all of a sudden, this big addition of 100,000 times as much energy is thrown at the Earth.
The CME creates immense electrical currents in the ionosphere. The upper atmosphere practically crackles with energy. The auroras light up the sky as far south as Texas. Rivers of charged particles flow through the atmosphere and induce powerful electrical fields 60 miles below at the Earth's surface. Suddenly, with no warning, a vast current jumps onto the power grid. The surge races through the system, and the network overloads. The lights go out in Quebec.
We're talking about thousands of components in a power grid that are affected simultaneously, and there really is no place to run and hide from the effects.
The Quebec event was rare, but not unique. So how at risk are we? And when will the next solar storm strike?
For solar storms, it's always a question of when the next one will happen. It's not a question of will they suddenly go away.
To gauge the future threat, scientists need to know how often the Earth has been hit in the past. The hottest storms in the solar system have left their mark in one of the coldest places on Earth, the Arctic Circle. Locked within layers of ice is a history of the Earth. The ice keeps a record of solar storms dating back thousands of years. To see how often the storms hit, researchers look for a chemical they leave behind: nitrate.
You can actually core the ice and measure the nitrate abundances, and you find that the spikes in the abundances match up very nicely with some of the more recent intense storms.
By scanning ice cores, scientists travel back to an age when a massive solar storm struck Earth. A huge peak in nitrate reveals a solar storm that makes the Quebec event look like a firecracker.
The most intense abundance change that we see in the ice core data occurred in September 1859. It was so intense that we call it a superstorm event. It knocked out telegraph service in North America and most of Europe, and it was also seen all the way down in Calcutta, India at the time. It was a major worldwide event seen just about everywhere.
The 1859 storm is the most powerful solar eruption to hit Earth in 500 years. It's 3 times stronger than the storm that blacked out Quebec. If it had hit today, it would probably be catastrophic.
When you think of all of the services that rely on electric power, it's rather staggering to imagine the kind of a geographic footprint that one of these storms would have.
After a superstorm, the lights don't come back on the next day.
Most of the transformers that are used by the big power grids are custom order and can take months to replace.
Imagine months without power. Transportation grinds to a halt. The economy nosedives. No running water. No sanitation. Scarce food. Rampant disease. From the space age to the Stone Age, in the blink of an eye.
A solar storm would affect the power grid in an entire continent because these kinds of storms span the entire planet. It's unlikely that in your lifetime or mine, we're going to see one of these superstorm events. After all, the ice core data was 500 years long, and there was only one of these events in 1859. But there are plenty of events that were half as strong or even a third as strong. They are more numerous, and because of that, the long-haul effect of these things could be actually substantially worse than one major storm all at once.
It could be worse. The sun isn't the only star that produces solar storms. Astronomers peer far into the depths of space and watch stars being born and others die. A chance discovery shows just how dangerous space can be. Astrophysicist Eric Feigelson is researching deep space, looking for streams of X-rays. But what he stumbles upon blows his mind.
Instead of finding what we thought we would find, we instead found these rapidly changing X-ray sources associated with young stars. And we were quite puzzled, frankly, for some years.
The stars produce mysterious bursts of monstrous X-rays, solar flares out of this world.
So the strongest flares we've seen are 10,000 times stronger in the X-ray band than the strongest flare ever seen in the sun. When we looked at 1,000 young suns simultaneously in the Orion Nebula, we found that they're typically flaring at this level once or twice a week.
Solar storms like the one that hit Quebec can release as much energy as 1 billion atomic bombs. The star's Feigelson studies produce flares 10,000 times more powerful. The Hubble telescope catches an eruption on a star 450 light-years from Earth. This flare is so huge, if it hit a space colony, it would take out more than their power. It would take out their planet. Scientists call it a superflare. It's not just one star that creates superflares. There are regions of space where nearly all the stars are doing it. 1,500 light-years away is the Orion Nebula. It's a brilliant haze of gas and dust. In X-ray, the dust disappears, leaving only the stars. This X-ray movie was filmed over 13 days. Each tiny flash is a flare thousands of times more powerful than any produced by our sun. These stars are just like the sun, except much younger.
This cluster was formed about 1 million years ago. Now, that may sound like a long time ago, but compared to the sun, which is 4.5 billion years old, these are very, very young stars.
The Orion Nebula is where new stars are born.
They'll all become like our sun. They're just like our sun was when it was a young star.
Space scientist Gibor Basri wants to know why young stars create such huge flares.
If you take a given kind of star, say a star like the sun, there's a direct correlation between how much magnetic activity you see on that star and how fast you spin it. The slower the star spins, the less activity it has on it.
Like the sun, these stars create huge amounts of magnetic energy because their equator spins faster than their poles. The faster a star spins, the bigger the arcs, and the stronger the flares. And young stars spin very fast.
Our sun goes around about once a month. When it was very young, it went around every couple of days or a few days. So that's how much it's slowed down. And that means that the sun is now much less active than it was then.
Feigelson describes a sun we wouldn't recognize.
When the sun was a baby star at 1 million years old, it was 3 times bigger. It was a ruddy orange color. It had huge star spots that whipped around every few days, rotating much faster than it is today. And the magnetic fields, which you wouldn't see with your visible eyes, but you'd see with an X-ray telescope. The magnetic fields would be 10 times the size of the star, crackling and seething with explosions.
Some scientists think if it wasn't for the violent early sun, the Earth and all the planets in the solar system might not be here. 4.6 billion years ago, the solar system is just a cloud of gas and dust racing around the young sun. How it transforms into the solar system we see today is still a mystery.
So the disk is full of dust, and it's sort of the consistency of cigarette smoke. These are really tiny dust particles. We're really pretty puzzled about how you get from dust bunnies to asteroids. It's easy to stick snowballs together, but it's not so easy to stick sandballs together.
Basri thinks the violent young sun helps build all the planets in our solar system. Giant solar storms rip through the disk. The dust particles are forced together. Over time, they fuse and grow. The first embryonic planets are born. Eventually, the solar system is formed. And as the sun ages, it begins to slow down. If it hadn't calmed, life in the solar system might never have developed. Yet when the sun coughs, the Earth still shudders. There's little shelter from the effects of a massive solar storm. The only way to protect our electricity network is to shut it down before the storm strikes. But how do you predict a solar tantrum? Solar storms are a serious threat to our high-tech lives in the 21st century. The race is on to predict when and where the next one will strike. In September 2006, Japan launches the Hinode satellite. Its 3-year mission is to map the sun's complex magnetic fields. The information it sends back could prove key to forecasting solar storms. Hinode orbits 370 miles above Earth. Its camera peers straight into the sun's atmosphere. It returns the clearest pictures ever of the sun's surface. In December 2006, Hinode captures this groundbreaking footage. A magnetic arc snaps, and a huge flare erupts. It blasts into the solar system at more than 1 million miles an hour. Carol Schreiber uses data from Hinode to generate the first computer model of a solar storm before it erupts. A detailed map of the sun's complex magnetic fields.
What drives these large solar flares is the magnetic field, and specifically its electrical currents running through the magnetic field. So each one of these strands is essentially an electrical current prefabricated in the interior of the sun, breaking through the surface and becoming visible, and then ready to power a flare.
Where the magnetic fields intertwine the closest, the currents are strongest. Schreiber replicates these electrical currents in 3 dimensions.
If we tilt this, we can suddenly see that these electrical currents come up from one place, go up by something like 20,000 kilometers above the solar surface, and come down again.
The model shows a red river of energy equal to 1 billion atom bombs. When the flare erupts, it releases that energy in seconds.
The amount of energy that goes off in this flare is simply astounding. It's the equivalent of 1 million times 1 million atomic bombs going off at the same time.
If Hinode can spot these densely packed lines of magnetism before a flare explodes on the sun, scientists might be able to predict when the next solar storm will strike. Until that technology arrives, space weather forecasters use a method of analyzing the sun's activity developed almost 400 years ago. Sunspots. Sunspots form because the sun's atmosphere is hotter than its surface. The magnetic arcs block the atmosphere, making the sunspots burn cooler than the surrounding surface. 6,300 degrees versus 10,000 degrees. Sunspots come and go in an 11-year cycle of maximums and minimums. Solar minimum has few sunspots and the fewest flares. At solar maximum, 200 sunspots or more, all firing magnetic arcs. A week before the Quebec blackout, astronomers identify a group of sunspots on the eastern edge of the sun's surface. The blackout occurs during a solar maximum. The next maximum is around the corner, in 2012. The sunspot cycle tells us the gun is loaded. It doesn't tell us when or where the bullet will strike. Once the magnetic arcs cross, the trigger is pulled and a flare explodes. It reaches Earth in just 8 minutes, too fast for a warning. But the most damaging part of a solar storm is slower. A coronal mass ejection can take up to 4 days to arrive. If we know when the solar surge will hit, we can save the electricity network by shutting it down. At the Space Weather Prediction Center, scientists keep a watchful eye on the sun. They're looking for any increase in activity, including the buildup of sunspots.
Well, the forecaster today is looking at the data, trying to understand what the sun is doing right now, and then making predictions of the effects on Earth.
Solar satellite technology is young. It's observed the solar maximum only 3 times. Space weather forecasting is where Earth weather forecasting was 50 years ago.
If you were trying to predict a hurricane, if you didn't know anything about the speed of the winds and you didn't know anything about the atmospheric pressure at the eye of the storm and some of those types of things, that would be fairly comparable to where we are now in space weather.
You can see a hurricane coming, not a solar storm. Once it leaves the sun's surface, it's practically invisible. It can hold 10 billion tons of matter, but it's spread over millions of square miles. Just a handful of atoms in every cubic foot.
You couldn't see one of these storms arriving at Earth with the naked eye. They are so dilute that they are actually better than the kinds of vacuums that we can create under laboratory conditions.
Satellite instruments are sensitive enough to detect solar storms, but there's a catch. If one heads straight toward us, it's very difficult to tell how fast it's traveling. It's like the batter in a baseball game. As the ball hurtles toward the hitter, it's impossible to judge its exact speed. 3 strikes, and he's out. If scientists misjudge the speed of a solar storm, 1 strike could take us back to the Dark Ages. To help solve this blind spot, in 2006, NASA launches a 2-stage satellite called Stereo.
Stereo's great. We're going to be able to watch coronal mass ejections from perspectives that we've never been able to see before. And most importantly, it would be the one that allows us to watch the event happen along the Sun-Earth line.
After launch, the satellites separate. They use the moon's gravity to reach their orbits, flanking the Earth. The 2 near-identical satellites orbit the sun, but one of them is slightly ahead of the other. They give the first 3-dimensional stereo view of the sun. Scientists can now forecast very quickly if and when a solar storm is going to hit the planet.
It will improve the timing in particular of the forecasts that we would try to make, to mitigate the consequences of that as it went by the Earth.
NASA hopes that Stereo's information will lengthen early warning times from just a few hours to a couple of days. It could prevent blackouts like Quebec from ever happening again. One day, advanced satellite technology might even predict solar storms before they're born.
It won't be next year. It may be a few years, but it's doable now. We've been moving ahead very rapidly with less and less simplifications, with bigger and bigger resolution, more finesse in the models. And we're getting to a state that we can say that we're actually approximating what really happens on the sun.
Stereo could save our way of life from solar storms. For 2 million years, solar storms did us no harm. Less than 2 centuries ago, we harnessed electricity and got our fingers burned. Nobody knows exactly when the next solar storm will strike. Solar maximum is just 3 years away, and once again, Earth could be in the firing line. Hopefully, this time, the lights will stay on.
Imagine a world frozen solid, encased in ice from pole to pole. No life roams these frozen plains. Only glaciers move across them. This is not some distant planet starved of sunlight. According to a radical theory, this was Earth, 650 million years ago. No one knows what triggered this calamitous freeze. But if it happened once, could it happen again? Imagine the most profound ice age you can think of. Temperatures plummet to below zero, even at the equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
Snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
We would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Incredible though it may seem, the Earth may have frozen over completely. Scientists are finding clues in unexpected places. The story begins with a mystery. In the arid Flinders Ranges in southern Australia, layers of ancient rock hold unusual stones. These stones are foreign to the area. They are known as drop stones. The drop stones are embedded in an ancient sedimentary sea floor that formed around 650 million years ago. Tim Raub, a geologist at the Californian Institute of Technology, hunts for these drop stones at the Flinders Range.
This is an example of a drop stone, a piece of ancient rock that was dropped into the ancient mud on the sea bottom.
These drop stones are visibly different from the sedimentary bedrock around them. Something powerful must have carried them here. But what? Dan Schrag, professor of Earth and Planetary Sciences at Harvard University, believes the answer is glaciers.
We actually have ice cubes here that we've made with pieces of sand and gravel in them. So these ice cubes are like the glaciers that are taking rocks from the land, and then when we put them in the water, they'll actually melt and the sand and gravel will fall to the bottom, just like the drop stones on the ocean floor.
These drop stones are evidence that at some point, this area was covered in a thick layer of ice. But it's difficult to explain how ice could have covered the sun-baked mountains of southern Australia. Unless the continent itself was in a very different place. The continents haven't always been where they are now. They move very slowly across the Earth due to the movement of tectonic plates. 650 million years ago, around the time the Flinders dropstones landed here, the continents were positioned very differently. Since the dropstones formed under ice, perhaps Australia sat nearer to the poles where temperatures were lower. To locate the position of a continent in the distant past, scientists study the magnetic identity of rocks. Certain sedimentary rocks contain magnetic particles. When the rocks form, these iron particles line up with the Earth's magnetic field. Near the poles, they align at right angles to the sedimentary layers. And around the equator, they align parallel to the layers. Even if the rock moves, the distinctive configuration of these magnetic particles remains the same and provides a kind of geological fingerprint of the rock. Professor Joe Kirschvink at Caltech Pasadena is fascinated by magnetism.
Magnetism is magic. I've even named my eldest child after a magnet, so I enjoy magnetism.
Kirschvink and his team analyzed the 650-million-year-old rock surrounding the dropstones. The results were unexpected.
That part of Australia was within 5 degrees of the equator, and it just was the most weird place to expect a glacier.
But Kirschvink had to be sure that this ancient rock still held its original magnetic signature. If the rock heated up after it formed, its native magnetism would have changed. Back at Flinders Range, Kirschvink's team uncovered clearly striped sedimentary rock that provided proof.
Here, tens of thousands of layers of mud grew one at a time, upward and upward, in a glacial lake at the edge of a 635-million-year-old ice sheet.
When this rock formed, layers of sediment built up in distinctive horizontal lines. By comparing the direction of the layers of sediment with the direction of the lines of magnetism, Kirschvink could determine whether the rock's magnetic signature had changed.
We can explain the process of magnetism with a simple eraser. If the rocks formed on the equator and gained their magnetism very early, we would expect the magnetic direction to be parallel to the bedding very precisely like this. And then, since the rocks are soft, if they get squeezed or deformed geologically, you would expect them to rotate like this, and the magnetism would shift with the bedding. On the other hand, if the rock had been squeezed and deformed first, and then gained the line of magnetism like this, we would see them warped relative to the bedding today.
If the rock still had its original magnetic orientation, the lines of magnetism would follow the lines of sediment. But if its orientation had changed, the magnetism would cut through the sedimentary layers. Raub drills into the formation to retrieve solid cores of the rhythmic rocks. Back in the lab, the team analyzes samples of rock using a custom-built hypersensitive magnetometer. This magnetometer measures the orientation of the magnetic particles in the rock. It confirms that the particles were aligned with the rock layers. Kirschvink was astonished.
Quite frankly, when I saw the original study, I didn't believe it. And what in fact we see is that they're like this, and as the rock was warped, magnetism warped. That proves conclusively the magnetism formed before the rock was solidified.
This discovery seems to provide irrefutable evidence that the glacial rocks formed close to the equator. Paul Hoffman, professor of geology at Harvard University, was intrigued.
So if there were glaciers close to the equator, where the temperature was warmest, one has to assume that there was also ice in higher latitudes where the temperatures were colder.
650 million years ago, Australia sat near the equator. And yet evidence suggests that its arid rocks lay buried beneath ice. And if there was ice at the equator, there would have been ice all over the globe. These dropstones became the catalyst for a radical theory: Snowball Earth. This is a theory about the most extreme ice age imaginable. And if it happened before, it could happen again. Our world has been through many periods of extreme climate change. But some scientists have proposed that 650 million years ago, the Earth may have frozen over completely. This radical hypothesis raises one crucial question: how could it have happened? Kirschvink proposes that the giant freeze was triggered by the same mechanism that lies behind today's global warming, the greenhouse effect. Except 650 million years ago, it worked in reverse. Greenhouse gases in our atmosphere act like an insulating blanket, trapping the sun's energy to keep Earth's temperatures mild. When the snowball began, scientists suspect that levels of these vital gases fell dramatically.
The Earth's atmosphere might have been filled with methane and carbon dioxide, and the Earth became addicted to this high level of carbon dioxide and methane in order to keep its temperature. Then, if some unknown event crashed the carbon dioxide out of the atmosphere, Earth might have run away into a snowball Earth.
If enough carbon dioxide had been pulled out of the atmosphere, an anti-greenhouse effect would have plunged the Earth into a deep freeze. But this theory is only possible if there's a mechanism that could pull all the CO2 out of the air. In fact, carbon dioxide is removed all the time through a process called silicate weathering.
Weathering is a geological term for the decomposition of rocks under the influence of the weather. It's a process that converts solid rock into soil. Now, its importance for the climate is that weathering consumes carbon dioxide, which is a major greenhouse gas in the atmosphere.
Carbon dioxide reacts with water vapor in the atmosphere to form carbonic acid rain. This acidic rain weathers limestone on land and carries away the eroded sediment to the sea. Here it builds up, eventually forming limestone on the sea floor.
So the presence of the limestone is the evidence that weathering is occurring.
The more carbon dioxide gets locked away in limestone, the cooler the Earth becomes. But if this is happening all the time, something must have amplified the process for the whole world to have frozen over. Again, clues lie in the position of the continents. The movement of tectonic plates continually shifts the continents around the globe. Today, a lot of the continents are located in higher latitudes. If the Earth cools, the continents near the poles ice over. The ice prevents the rocks beneath from being weathered by carbonic acid rain. This means that the weathering cycle is kept in balance. With less carbon dioxide locked away in limestone rock and more in the atmosphere, the planet warms. Scientists have worked out that 650 million years ago, the continents were clustered around the equator, where it's warm and wet. Consequently, the global rate of weathering would have been higher.
During the Snowball Earth, we suspect that there were many more continents at the equator, and this would actually lead to a situation that would make the planet vulnerable to a global glaciation.
As the Earth cooled, ice formed at the poles. But because there were no continents in the higher latitudes, ice accumulated on sea rather than on land. There was nothing to regulate the weathering. The cooling continued unchecked, and the world got colder and colder. This runaway scenario is certainly plausible. But although extreme weathering could be behind an ice age, it doesn't explain how the Earth could have iced over completely. Geologist Galen Halverson from Adelaide University studies triggers of the snowball.
One of the hardest parts about understanding the snowball is really how it began. We think that it must have began like a normal glaciation.
Normally, living things help to regulate the Earth's climate by maintaining the delicate balance of carbon dioxide. Plants consume carbon dioxide. Animals produce it. These consumers and producers help to regulate the climate, ensuring the Earth is neither too hot nor too cold. If there's more carbon dioxide in the atmosphere, it gets warmer. This causes plants to grow faster, which in turn draws out more CO2 from the air.
So that is a feedback against it getting too warm. And in reverse, if it starts getting too cold, then the biosphere responds by not drawing down as much CO2, and that allows CO2 to go back up. So there's a sort of buffer in the form of life on Earth that prevents temperatures from getting too cold or from getting too hot.
But rewind 650 million years and witness a very different story. Life on land was in its early stages of evolution. Most living things were in the oceans. This half-formed biosphere could not prevent the Earth from swinging to wild extremes of temperature. Colonies of single-celled organisms called cyanobacteria were the first to photosynthesize. They pulled carbon dioxide from the surrounding water to precipitate calcium carbonate, and they used this to make dome-like structures of rock. Geologist Jim Gehling is an expert on these early life forms.
Temperatures were dropping at this time, 650 million years ago, for the very good reason that carbon dioxide, the principal greenhouse gas, was being taken out of the atmosphere and locked away on the sea floor.
This trapped carbon dioxide can still be seen today in stromatolite reefs.
This is actually solid carbon dioxide, and I can release that carbon dioxide after all those hundreds of millions of years when I put this weak acid on the rock. And there you see it erupt as the white bubbles of carbon dioxide spring out of the rock, go back into the atmosphere to take up their role all over again as greenhouse gases.
The more carbon dioxide the cyanobacteria locked away, the cooler Earth became. Our planet was hurtling towards a deep freeze that would last for millions of years. $650 million years ago, the Earth's temperature plummeted. Huge sheets of ice spread across the planet. Eventually, they engulfed most of the land and sea. This was no regular ice age. Ice ages are nothing out of the ordinary. We experience them every 100,000 years or so. They are mainly caused by small changes in the Earth's orbit, which alter its position relative to the Sun. When our planet receives less of the Sun's energy over a number of years, ice forms high in the northern hemisphere and advances down. At the height of the last ice age 21,000 years ago, these icy sheets reached down as far as New York. But the tropics stayed warm. Only about 30% of our planet froze. But 650 million years ago, some scientists believe the ice kept coming, until eventually, most of the globe was covered. What could have caused this runaway cooling? The answer must lie in how our planet keeps or loses the sun's energy. The Earth's surface is made up of land, open ocean, and ice. These all reflect sunlight to a different degree. The amount of light a surface reflects is known as its albedo. Deep dark ocean has a low albedo, since it absorbs a lot of sunlight. White snow and ice have a very high albedo, since they reflect more of the sun's energy back into space. Tim Raub demonstrates how dark and light colors heat up under the sun.
The temperature of a white car sitting in the sun is only 120 degrees. The temperature of a black car sitting in the sun is 144 degrees. The black car absorbed light, the white car reflected it.
White reflects more sunlight, keeping whatever it's covering cooler. The more ice that covers the Earth, the more of the sun's energy reflects back into space, and the colder the planet becomes. This cooling leads to more ice forming, which further increases the surface albedo. This is known as ice albedo feedback. And something may have accelerated this cycle of cooling even more. New research suggests that when seawater freezes at very low temperatures, its composition changes, and it can become more reflective. At the University of Washington's Polar Science Center, Bonnie Light studies the relationship between ice and light. In the cold room, she freezes buckets of salt water at different temperatures. One of the buckets is exposed to Snowball Earth temperatures of -10 degrees. The surface of this ice becomes much whiter.
Okay, so this bucket contains seawater that was frozen in a cold room at 5 degrees above 0 Fahrenheit. And we consider this a good laboratory analog for modern day sea ice on planet Earth. And you can see that the surface of it is kind of gray colored, dull appearance. And this bucket also has salt water in it, although this salt water was frozen at about 10 degrees below 0 Fahrenheit. And we consider the ice in this bucket to be a good analog for sea ice on Snowball Earth because it's very cold.
At Snowball Earth temperatures, the composition of sea ice changes, turning its surface from gray to bright white.
And you can see that these crystals in this case have started to collect at the surface of this cold ice. And so I can kind of scratch away these crystals, and you can see that this is basically just a deposit on the surface of this cold ice.
At -10 degrees, salt molecules in the ice begin to form tiny crystals.
If you can isolate them under the microscope, they look like little gemstones. They're really quite beautiful.
These bright crystals have a dramatic effect on albedo. The white surface scatters more of the sun's energy and reflects it back to the atmosphere, causing temperatures to drop even further. In the 1960s, Soviet climate modeler Mikhail Budiko demonstrated how runaway ice albedo could cause a cooling Earth to freeze completely. Like many of his contemporaries, Budiko was worried about the effects of a nuclear winter. Nuclear explosions create clouds of smoke and dust, which block the sun's energy and lower the Earth's temperature. Budiko developed a mathematical model to work out the odds of a global ice age. He showed that if the Earth's climate cooled enough for ice to form in the lower latitudes, then the ice albedo would rise at a faster rate. And once the glaciers reached a certain latitude, the Earth would tip into a snowball-like state.
Somehow or the other, the ice line, the glaciers, reach some critical latitude, around 30 degrees. And once they hit that latitude, very, very rapidly, the Earth would have been entombed in ice.
Budiko's groundbreaking work showed how this snowballing effect could create a totally frozen planet within just a few decades.
Budiko's work was extremely important in demonstrating that it was possible that Earth might slip into a climate catastrophe which was covered completely with ice. It had not been recognized as a possibility before that.
If the Earth became entirely covered in ice, nearly all the heat it received from the sun would be reflected back into space. The planet would become locked in ice. So if runaway freezing trapped the Earth in ice, how did it ever escape? Some scientists suggest that 650 million years ago, our entire planet was locked in an extreme ice age. It was a unique event, the result of a set of improbable triggers. Or so they thought. Then, in 1997, evidence emerged that it could have happened more than once. It came from glacial deposits in South Africa that were over 2 billion years old. Paleomagnetic evidence suggests that these formed near to the equator. Geologist Paul Hoffman believes this could be proof that the Earth froze over completely at least twice in its history.
The best evidence for a snowball Earth 2.22 billion years ago is paleomagnetic evidence from South Africa. There are glacial tills there, boulder clays, that formed very close to the equator.
This discovery raised the possibility that the snowball wasn't a single event, but a recurring condition. Scientists raced to find the trigger for this earlier deep freeze. The cooling appeared to coincide with the Great Oxidation Event. Deep in the ocean, some of the oldest organisms on Earth evolved a mechanism called photosynthesis. The ability to convert carbon dioxide into oxygen using the sun's energy. As these photosynthesizing microbes thrived, they had a profound effect on the Earth's climate. 2 billion years ago, our sun was weaker. Our planet relied on greenhouse gases like carbon dioxide and methane to maintain its temperate climate. But photosynthesis uses up carbon dioxide. It also produces oxygen, which destroys methane. The result, a double whammy. Levels of both these vital greenhouse gases plummeted.
You have a precarious situation. You have a planet that's greenhouse needs methane, and you suddenly evolve a bug that destroys the methane.
Maybe the first bacteria that photosynthesized crashed the carbon dioxide and methane from the atmosphere and triggered the first snowball Earth.
As oxygen production soared, methane levels tumbled. With the loss of that greenhouse gas, the Earth spiraled into a deep freeze.
It's kind of a frightening conclusion that a single-celled mutant bug destroyed an entire planetary ecosystem. Destroyed it. Turned it into a snowball for maybe 35 to 100 million years.
Some scientists now think that our planet has been encased in ice on at least 3 separate occasions, and each time under different circumstances. But these snowball Earth scenarios present a huge problem. If our planet was trapped in ice, how did it ever escape? Something must have caused a global meltdown. Evidence of the thaw is right here. On top of the dropstones sit layers of a peculiar reddish-gray rock. These layers stretch for miles in the Flinders Range, Death Valley, and almost everywhere where the glacial rocks appear. These are carbonate rocks, which form in warm, shallow seas. But here, they appear right on top of the glacial deposits.
So here's a sample that actually shows the end of the snowball event. So that's an ice-rafted stone dropped out of an iceberg. And these are little grains that also fell out of an iceberg. And immediately on top of that, without any break in sedimentation, is cap carbonate that's precipitating directly out of the ocean and accumulating on the seafloor. And exactly the same relationship is seen all over the world.
Their presence is evidence of a sudden and drastic temperature increase. Only one thing could have triggered this: a huge injection of greenhouse gases such as carbon dioxide. In order to melt Snowball Earth, concentrations of carbon dioxide had to be around 350 times higher than they are today. But if the whole planet was encased in a thick layer of ice, where did the carbon dioxide come from? Caltech professor Joe Kirschvink had a revelation.
I woke up in the middle of the night and said, that's got to be it. It just dawned on me that these subaerial volcanoes, like in the Aleutians and Yellowstone, these volcanoes sit and they spew CO2 into the air.
Even beneath the ice, volcanoes would have continued to release immense volumes of carbon dioxide. With the rest of the planet still ice-locked, there would have been no mechanism to remove it from the atmosphere. Over millions of years, levels of this greenhouse gas would have built up, eventually producing enough warming to offset the ice albedo. The ice melted, sending global temperatures spiraling upwards. As this melted ice water evaporated, it swelled the atmosphere with moisture, creating torrential rainfall. Carbon dioxide in the atmosphere acidified the rain. Acidic downpours rapidly eroded limestone, washing sediment down into the oceans. Here, layers of carbonate sediment accumulated on the sea floor to become carbonate rock. Dan Schrag demonstrates what could have happened.
Instead of carbonic acid from carbon dioxide, we're going to use a little stronger acid to make it go a little faster. This is nitric acid, and when we add it to the limestone, it will dissolve away the limestone and ultimately create a very clear solution. So you can see it bubbling away. And when this is added to the ocean, it reacts and creates the cap carbonates that blanket the top of the glacial deposits.
But still, not everybody is convinced that the planet was ever entirely covered in ice. Some scientists argue that the chances of life surviving a full-on snowball are virtually nil. Above the ice, the freezing conditions were too hostile, while below it, life was cut off from sunlight. Yet there is evidence that photosynthesizing organisms did survive the freeze. Single-celled cyanobacteria existed right the way through. Cyanobacteria can survive extremes of temperatures many degrees above and below zero. But if the oceans froze over, a thick layer of ice would have sealed them away from the sunlight. With their energy source blocked, they would have died out.
If you'd been diving on a tropical reef before Snowball, this is what you would have seen. Slime world, mounds of slime on the sea floor. And if you touch them, you'd find out that they're actually rock. A surface covered with slimy material, which is actually cyanobacteria, the earliest, the most primitive form of life that's been around for 3 billion years up until this point and is still around today.
Critics argue that nothing could have survived the ferocious conditions of a total global freeze. They maintain Snowball Earth was nothing more than a severe ice age with extensive glaciers and a belt of open water around the equator. Philip Allen, a geologist at Imperial College London, believes that the evidence for a frozen planet is flawed.
I am not in agreement with the Snowball Earth hypothesis. The major hole in the theory, as far as I'm concerned, is that the sedimentary rocks deposited during the glacial periods do not support the idea of a long-term global freeze.
Philip Allen's counter-evidence includes the ripple-like patterns in rocks formed 650 million years ago.
When you look at those sedimentary rocks, it indicates open water. The wind was able to blow over the water surface and form ripples, wave ripples on the seabed. So they are really conclusive proof of an open water surface rather than an ice-covered one.
Waves in an open sea left imprints in the sediment of the sea floor. When the water disappeared and the sediment turned into rock, the ripples remained. Allen and others propose an alternative to the Snowball Earth. It's known as the slush ball. In their version of events, the Earth never froze completely. Some patches of open land and sea remained. But proponents of the snowball theory don't suggest that the frozen planet was without any open water. Schrag believes that life could have survived in ice holes around sources of geothermal energy.
Even in a completely ice-covered planet, there's still plenty of places where there are hot springs, geothermal heat from volcanoes, probably thousands and thousands of such little holes. And in many of those little holes, you could sustain life throughout the Snowball Earth period.
The reality is, we may never know if the world was ever completely frozen over.
Sometimes people think of the Snowball Earth like a cartoon, an oversimplified planet. But the real world is much more complicated than that.
Whether slush ball or snowball, everyone agrees there was a profound global freeze. And when our world emerged, 635 million years ago, something unexpected appeared. Life. Far more complex than anything that had gone before. After the Big Freeze, life on Earth exploded. Our planet, 650 million years ago. Temperatures plummeted, turning our planet into a hostile place. Yet somehow, life survived. And as soon as the frozen Earth began to thaw, it blossomed. And there was an unprecedented explosion of life on Earth. Before the deep freeze, life was primitive. Single-celled organisms and algae were mostly confined to the oceans. Shortly after it ended, the first multicellular animals appeared. The big question is, did the global cooling trigger this great leap in evolution?
Well, the best evidence is the coincidence in timing. The fact that the first fossils of multicellular animals occur less than 3 million years after the last snowball termination.
Shu-Hai Xiao is a geologist at Virginia Tech. He unearthed some of the oldest multicellular animal fossils in the world in a mine in southern China.
The fossils are really small. They're about ½ millimeter in diameter, so you can barely see them with naked eyes.
Under a microscope, he discovers that the fossils are very primitive animal embryos. Some fossils show clusters of 2, 4, 8, and more cells.
It was really exciting when we found those. Those are some of the earliest animal fossils, and they have found in rocks that were deposited almost immediately after the Snowball Earth ended.
Fossils of these animal embryos date back to just 3 million years after the global freeze ended. That might seem a long time in human terms, but geologically, it's the blink of an eye. Over the next 80 million years, animal life exploded. In the Flinders Ranges in southern Australia, geologists have found some of the oldest fossil evidence of complex multicellular life. These creatures bear little resemblance to life today, but they offer clues to the genesis of early life. 650 million years ago, this area was beneath a shallow sea. Bizarre, soft-bodied organisms similar to jellyfish or flatworms lived on the sea floor. Some of the organisms got trapped in fine silt of tidal flows where they fossilized. Jim Gehling has been investigating these early animals.
Probably our ancestors lie in these rocks. This thing here, Dickinsonia, can best be described as some kind of a pancake or mat-like worm creature. It doesn't have a proper head. It has what appears to be a gut, very fine segments.
But this doesn't explain how the severe planetary freeze could have triggered a leap in evolution. What we do know is that there is a striking coincidence between the rise of oxygen and the end of the snowball. Oxygen levels rise following these global ice ages because of a chemical reaction between ice and sunlight. 650 million years ago, there was no ozone to stop the sun's ultraviolet light hitting the Earth's icy surface. This UV light reacted with water vapor to form hydrogen peroxide. The hydrogen peroxide remained in the ice for millions of years. But when the ice melted, the hydrogen escaped, and the peroxide converted into water and oxygen. Oxygen reached the same level as we have today. At roughly the same time, the first complex animals appeared. More oxygen enabled life to become multicellular. A single cell can take up gases and oxygen from water. Oxygen fuses across the cell membrane into the cell. However, when several cells link together, it's harder for oxygen to diffuse from one cell to the next. The pressure of oxygen needs to be higher.
You need to have a high enough pressure of oxygen to have a circulatory system bring the oxygen all around the body. After the last Snowball Earth, oxygen seems finally to have been high enough to support hundreds, thousands, millions of small early animals on the seafloor.
Oxygen turned out to be the linchpin of evolution. The ability to use oxygen enabled life to become dramatically more diverse.
Oxygen gives us 20 times more energy, or more than 20 times more energy, than any other thing that we can breathe, or that life can breathe. You can have bigger animals, you can have more active organisms, you can have plants that grow and transport liquids from roots to the leaves, and you can have birds energetic enough to fly. Without oxygen, we would all be slime.
A frozen Earth may have given early life a push forward. But if the world were to freeze over again, we'd struggle to survive. We know it's happened several times before. The question is, could it happen again? One factor in our favor is the sun. Over the last 4.8 billion years, it has been getting more and more active as nuclear fusion generates more and more heat. The sun today is about 6% warmer than 650 million years ago. So in the short term, another deep freeze is unlikely.
The sun is warmer today. That probably helps us out. But until scientists really understand what causes Snowball Earths, I don't think any of us know whether we're in danger or not of a recurrence.
But there is one possibility that could result in another global freeze: a shift in the position of the continents. We know their arrangement influences the climate. If the majority of the continents were clustered on or near the equator, the Earth would be more likely to turn into a snowball. Cooling temperatures would cause ice to form in the open ocean of the poles, while weathering would continue on the continents. With more and more carbon locked away, temperatures would plummet.
If all the continents were near the equator, then the Earth could get colder and colder, and sea ice could form and get to lower and lower latitudes, closer and closer to the equator.
Today, our world seems safe. Most of the continents are near the poles. But plate movement never stops. At some point, millions of years in the future, the continents may group around the equator once again.
I think it's possible someday, if the continents were in a very different position, maybe hundreds of millions of years from now, that we could indeed have another Snowball Earth.
It's unlikely that mankind will be around to witness another Snowball Earth. But the Earth will still be here. And just like it has in the past, our planet will survive and enter a new phase in its extraordinary history.
A split second, the Big Bang, and the whole universe was born.
In the blink of an eye, literally, so much can happen that it would blow your mind.
How did we get here? And what is the universe made of?
The secret of creation, the secret of everything is locked in that first second.
Technology stands on the brink of revealing what happened in the most important second of all time. In the beginning, there is nothing. No matter, no energy, not even empty space, because space itself doesn't exist. No time passes, because there's no such thing as time. From nowhere appears a fireball smaller than an atom. 10 trillion times hotter than the core of the sun. Everything that will become the universe explodes from a point millions of times smaller than a pinprick. Time begins. In 1 second, the blueprint for the entire cosmos is written. How it happened is the biggest mystery of all. Professor Lawrence Krauss has devoted his career to studying the first second after the Big Bang.
If we want to really understand our place in the universe, we have to go back to the very beginning and understand how it all came together.
Looking back to the instant of creation is a new idea. The theory of the Big Bang is widely accepted, but the concept is less than a century old.
But one of the things we have to put in perspective is how recent our understanding of the universe is. 80 years ago, the conventional wisdom in science was that the universe was static and eternal, had been around forever.
But this changes in 1929. At California's Mount Wilson Observatory, Edwin Hubble studies the light from galaxies. He observes that the farther the galaxy, the longer the wavelength of light it emits. Light waves stretch the more they travel, and stretching changes their wavelength. The same principle applies to sound waves. As a train approaches, the whistle's pitch rises. When it passes, the pitch lowers. As the train recedes, each sound wave has to travel farther than the last to reach your ear. The sound waves stretch, lowering the pitch. Something similar happens with light waves. If a galaxy is moving away from us, its light waves stretch, becoming longer and redder. It's called red shifting.
When we look at visible light, there's red at one end of the spectrum and blue at the other. Red radiation is the long wavelength radiation of visible light, whereas blue radiation is the short wavelengths. And as we look at the universe, we see the radiation from distant stars literally stretching so that the light gets redder. And the farther away we look, the redder the light is.
Galaxies around us have shifted to this red light.
We look out in all directions at distant galaxies, they're all moving away from us.
Nearly all galaxies are receding at 1 million miles an hour. If galaxies are speeding away from each other, at some point, they must have all been together. The universe is expanding outward from a single point. It's the first evidence that the universe had a beginning. Hubble's findings lead to a radical concept: the Big Bang theory. Scientists believe that in the first second after the Big Bang, the building blocks were created for every star and planet in the cosmos. To prove it, they first need a new way to tell time.
We are thinking of fractions of time smaller than we think about in any other area of human activity, and smaller fractions of time than a race car or a sprinter or anything else. And what we've learned is that more can happen in a fraction of a second, in a blink of an eye, than you can imagine. It would just blow your mind.
Hours, minutes, and seconds are the basis of modern life. But events after the Big Bang happen in fragments of time far smaller than a second. To analyze what happens, scientists use a new measure of time called Planck time. 1 Planck time equals 10 to the minus 43 seconds. That's a decimal point, 42 zeros, and then a 1. It's an unimaginably small amount of time. Yet in this first tiny beat of Planck time, something happens that shapes the next 13.7 billion years. Out of the fireball, the 4 fundamental forces of nature form. Those forces underpin everything around us. Gravity is the reason stars and planets form. It rules the moon and tides and keeps us on the ground. Electromagnetism lights our cities, connects our phones, and runs our computers. And the 2 nuclear forces, strong and weak, bind the particles that make up our bodies and power the furnace of our sun. We're here because in the first second after the Big Bang, the 4 forces are created. Without them, the universe would be a featureless fog of radiation.
If there were no forces, nothing would happen. There'd be no television. There'd be no sports. There'd be no love, no hate, no human tragedy, all the things that make life worth living.
But in the first beat of Planck time, the 4 forces are still rolled into a single superforce. Gravity, nuclear, and electromagnetic forces have not yet divided. Physicist Michio Kaku studies how the forces split apart.
I like to think of it as a crystal, a beautiful symmetrical crystal, all the forces unified in their elegant simplicity at the beginning of time.
As our cosmic clock takes one more tick of Planck time, the tiny fireball universe expands. The 4 forces start to break apart. It's like rapidly cooling a super hot crystal. Cracks form.
It began to shatter into 4 pieces. The first piece to break off was gravity. Then the nuclear forces began to split off. And finally, we have this fragmented jewel of what used to be the superforce.
Those 4 fragments are still at work. Gravity keeps Earth in orbit. Nuclear forces make sunshine. And electromagnetic radiation, the light that bathes our planet. We're just fractions of a second into our journey, and already the foundations of our world are forming. The fireball universe. Still smaller than an atom, and 1,000 trillion degrees. To discover how the universe expands, scientists use telescopes so powerful they can see the past. When astrophysicist David Spergel looks up, he sees history.
As we look out in space, we look back in time. Light travels at a finite speed. So the light we see from the sun takes about 8 minutes to get here. We see the sun not as it is, but as it was 8 minutes ago. We look out the night sky, we see the nearby stars. They might be 10 or 20 light years away. We see them as they were 10 or 20 years ago.
The Big Bang was so powerful and so hot, remnants of that heat still survive. The heat began as super-hot X-ray radiation. As it stretched and cooled, it became visible light, shifting from blue to red, then becoming microwaves, and finally radio waves. This faint radiation shines down on Earth all the time. It's called cosmic microwave background radiation, or CMB.
The cosmic microwave background is the echo of creation itself. It's the embers, the afterglow of the original shock wave that created the universe. If we had microwave eyes, eyes that could see microwave radiation, then every night we would see the Big Bang coming out. Looking at the heavens, we would actually see an explosion.
More than 13 billion years later, we have a way to see this cosmic glow with the naked eye.
You take your TV set, switch it between channels. A couple percent of the static that you see on your TV screen is radiation from the Big Bang.
This cosmic radiation is a direct connection to the Big Bang. It also reveals the universe entered a new phase, less than a trillionth of a second after its creation. Cosmic radiation is the key to discovering what happens next. A few beats of Planck time tick by on our cosmic clock, and the fireball universe is transformed. One instant, the universe is billions of times smaller than an atom. The next, it inflates to the size of a baseball, growing more in this moment than in all the 13.7 billion years to come. Scientists call this rapid expansion inflation. And the evidence survives in the cosmic radiation left over from the Big Bang. Like static on your television, this cosmic radiation seems so constant and so even, it presents scientists with a puzzle.
When we measure the cosmic microwave background in that direction, its temperature is identical to its temperature in that direction. It's the same everywhere.
The only explanation is the universe inflates countless times faster than the speed of light. Inflation expands the fireball universe evenly, like a balloon blowing up, with a phenomenal breath of energy.
I try and imagine compressing a spring. I push it closer and closer and closer together so it's smaller and smaller and smaller, and I've stored a tremendous amount of energy in that spring, and when I let it go, it bursts out. And that stored energy drove an exponential expansion of space.
But if the entire universe is uniform from the first second after the Big Bang onward, how did the galaxies form? Planets and stars begin as clusters of particles. Over time, these particles of matter clump together under the force of gravity to form a dense mass. Earth began as a ball of particles that clumped together through friction and gravity. The sun that sustains life on Earth started out as a cloud of gas and dust. How did these clusters form in the first place? The early universe should be lumpy, not even. To link the formation of stars and planets all the way back to the first second after the Big Bang, NASA scientists like David Spergel developed the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite mission to measure the temperature of cosmic radiation in more detail than ever before.
While this radiation is everywhere, it's very faint. And to observe it in great detail across the whole sky, you want to get away from the Earth and any interfering sources of radiation.
7, igniters armed, green board, 5, 4...
NASA launches the probe in 2001.
Main engines start, and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
It could produce the best ever snapshot of the universe in its first second.
The launch was incredibly exciting, tense, An exciting moment to see it go up and then realize it was working.
WMAP sits 1 million miles from Earth. It's so sensitive, it can measure the temperature of cosmic radiation within 1/1,000,000th of a degree. For 5 years, WMAP analyzes the sky in minute detail.
It sits there with the Earth and Sun always behind it, staring out into space. The satellite's spinning very rapidly. It covers about 1/3 of the sky every hour, spinning and making maps of the leftover radiation.
WMAP tracks the Earth as it orbits the Sun and scans the temperature of the whole sky. It generates detailed temperature maps like this one, and it reveals something remarkable. The blue and red patches on this map of the entire sky are tiny ripples in temperature.
The little blue regions represent regions that are a few tens of thousands of degrees colder. Red regions are a little bit hotter, so you're seeing tiny variations in temperature across the sky.
WMAP looks back over 13 billion years. As the universe evolves, these tiny ripples develop into clusters of particles that get bigger and bigger under the force of gravity, becoming just dense enough to trigger stars and galaxies to form.
I mean, it really was what I think we all dream of when we go into science. Looking at things that no one's looked at before, learning really exciting things about fundamental questions. Questions like, what's the universe made of? What happened in its first moments?
This is a map of how the universe looked in the first second after the Big Bang. The template for today's vast cosmos.
When the picture of the cosmic microwave background radiation first came out, the press said, "Ah, the face of God." Well, let's be real. It's not the face of God. What it really is a baby picture of the infant universe. So the discovery of the cosmic microwave background radiation ranks as one of the greatest discoveries in all of science.
Less than 1/1,000,000th of a second after the Big Bang, the fireball universe rapidly expands. Now an ultra-hot globe big enough to sit in the palm of your hand, the universe is seething with energy and radiation. But as the palm-sized universe expands and cools, something new starts to form. Only a fraction of a second after the Big Bang, and the destiny of the universe is already mapped out. The sun burns because of forces forged more than 13 billion years ago. The stars and planets form from the way the universe rapidly expands. Science can trace everything we see today back to the first second of creation. But we're here because of what happens in the next few beats of Planck time. The universe is flooded with the building blocks of matter. So far on our cosmic clock, the early universe is nothing but energy. How did pure energy turn into matter? Everything around you is made of matter. What you're sitting on, the air you breathe, the whole planet is made of matter, and matter is made of atoms. And in the first second after the Big Bang, the ingredients for atoms are created. How matter appeared mystified scientists until 1905, when Albert Einstein comes up with our most famous equation. E equals mc squared. Einstein's equation tells us that energy, E, and mass, m, are different forms of the same thing. Matter and energy are interchangeable. Some scientists later used this equation to create the most destructive weapon in history, the atomic bomb. It offers a clue to what happened in the first second. In a nuclear explosion, particles of matter are ripped apart to produce an enormous amount of energy. During the Big Bang, the exact opposite happens. An enormous amount of energy turns into matter. Einstein's equation prompts a conclusion. As the baby universe expands and cools, the pure energy of the Big Bang converts into the particles of matter that make us. We're only a fragment of a second into our journey. The first particles of matter appear. The universe is 1,000,000 times hotter than at the core of the sun, still far too hot for particles of matter to bond and form atoms. Scientists face a puzzle. What is this early state of matter like? And how does it become the protons and neutrons that form every atom in the universe?
Atoms were impossible. Think of putting an ice cube in a steam bath. The ice cube would melt immediately. You cannot have ice cubes in a steam bath.
You can see the proof in a block of ice. When water is cold enough, it's a solid. Warm it, and you get a liquid. Heat liquid water, and it boils away into a gas, water vapor. Superheat the gas, and the energy pumped in rips the atoms apart. Likewise, the universe in the first second is so hot, only the building blocks of atoms can exist.
If you were to journey into the early seconds of the universe, literally you would disintegrate. You would literally fall apart, and even the debris, the nuclei of your bodies, they too would fly apart into subatomic particles. There would be nothing left of your body.
There's only one way to see these super hot building blocks of matter in the first second after the Big Bang. Scientists must recreate conditions of the Big Bang itself.
The inside of a star is measured in tens of millions of degrees, but the Big Bang was measured in trillions upon trillions of degrees, so we have no way to simulate the instant of creation other than with a particle accelerator. By slamming protons into other protons, we can create temperatures not seen since the beginning of the universe itself. So particle accelerators are the only game in town when you talk about simulating Genesis.
This is Brookhaven National Laboratory in Long Island, home to the Relativistic Heavy Ion Collider, or RHIC, a 2.5-mile ring designed to smash the nuclei of gold atoms at nearly the speed of light.
With the particle accelerator, you slam subatomic particles together. As a consequence, we get a tremendous shower of debris, and then we want to make sense out of it. We want to know what's inside that collision.
The energy of the collision is colossal. On a small scale, it reproduces the embryonic universe in the first second. How? By ripping nuclei into the protons and neutrons they're made from. The energy is even enough to rip the protons and neutrons apart. Inside, scientists discover the building blocks of matter, tiny particles called quarks. But they're so small and move so fast, they're hard to track. If scientists can figure out how quarks behave, they'll unlock the secret of matter itself. What they find could revolutionize medicine and relaunch the space program. The project starts in 2000. Colliding nuclei creates a chaotic spray of particles. It takes 5 years to analyze the data. The results come in 2005. They're shocking.
We were expecting to find a gas when we slammed gold nuclei into each other. So the shock was, it wasn't a gas at all. We found that it's more like a liquid. So this came quite a shock, because now when we begin to simulate the early universe, we have to get rid of this mental picture of a gas of subatomic particles. Now we know it's more like a liquid, literally like a soup.
When matter first appears in the universe, the quarks are so dense and so energized that the entire universe is like a liquid. The universe went from a glowing ball of energy to quark soup in less than a blink of an eye. The liquid universe is hot, dense, and violent, flooded with tiny particles in constant vigorous interaction. As our cosmic clock reaches a millionth of a second, the universe continues to expand and cool. It grows from the size of a baseball to the size of our solar system. Matter has materialized from pure energy. Without matter, none of us would be here. And in that first second, that very nearly happens. Something comes close to destroying all matter in the universe. Armageddon is brewing. A split second after the Big Bang, and the universe is flooded with the building blocks of atoms. These tiny particles of matter must survive in a battleground. Everything around us is made of matter formed from the energy released by the Big Bang. Every molecule, every atom, every quark. How we end up with a universe that consists of so much matter is one of our biggest questions. The particle accelerator may reveal the answer. When the first second is recreated, two types of matter are produced in equal parts. One is the type of matter we see around us. The other is its opposite, antimatter. Dr. Tara Shears explains they're two sides of the same coin.
This apple is made of matter. We know that every matter particle in the universe has an antimatter partner that was created in the Big Bang. Now, antimatter looks similar to normal matter, but not quite. In fact, it looks like the mirror reflection of matter. So an anti-apple looks like this.
If the universe was made of antimatter, it would essentially look identical to how it looks today. You and I would be made of antimatter, and anti-lovers would sit in anti-cars looking up at an anti-moon at night making anti-love, and it would be largely the same.
But matter and antimatter are mortal enemies. They can't coexist.
When we have a matter particle meeting an antimatter particle of the same type, then they annihilate, they explode together, they destroy each other. All the energy that the matter and antimatter particle have goes into one large explosion of huge, tremendous energy.
Fractions of a second after the Big Bang and the future of the universe is at stake, matter and antimatter are locked in a battle to the death. A millionth of a second after the Big Bang, and a battle rages. When matter and antimatter clash, the result is explosive. Just one apple-sized clump of matter hitting its antimatter equivalent would release as much energy as a 10-megaton nuclear bomb.
If you could go back to the really early universe just after the Big Bang, you'd find yourself in this seething mass of matter and antimatter annihilating each other. You'd find yourself in the middle of this cosmic battle between both sides, caught in the crossfire, if you like.
With all the particles in a super-dense liquid state, matter and antimatter quickly meet and destroy each other. Since they're created in equal numbers, and every matter particle that hits an antiparticle is annihilated, all matter should be destroyed as soon as it's created.
All the matter would have eventually found the antimatter, and they would have annihilated, producing pure radiation. And we'd now have a universe. I was going to say we'd now be living in a universe of pure radiation, but we wouldn't be living in such a universe because we wouldn't be here. There'd be nothing but radiation.
But the universe is full of matter. How did it defeat antimatter? It's one of science's great mysteries. One theory is that antimatter is less stable and decays more quickly, creating a tiny imbalance between matter and antimatter. This tiny imbalance eventually allows matter to overwhelm antimatter. Whatever the truth, something happens just after the Big Bang that tips the balance in favor of matter.
And the whole battle stopped at that point, and what was left was a very small amount of matter. And it's that small amount of matter that makes the universe that we live in now. That means that we're the leftovers of this battle. We're the dregs. We're what's left when everybody else had finished.
The dregs go on to form everything around us. From the ground beneath our feet to the most distant galaxy. As the cosmic clock nears the end of the first second, nature's four forces have split off from the single superforce. The winner of the matter and antimatter war has been decided, and the subtle ripples in temperature that stretch across the universe mean that over the next billion years, gravity gathers clumps of matter to form galaxies. But one mystery remains, and it's a big one. We know how the building blocks of matter form, but we don't know what gives everything in the universe substance. We know so much about the first second, but a piece of the puzzle is missing. What gives everything in the universe mass? Mass makes it tough to get something moving, and makes it hard to stop. When we're pulled down to Earth, gravity is acting on our mass. On the Moon, gravity is weaker, so astronauts move slower. But their mass is the same as back on Earth. Even if an object weighs nothing, it still has mass. Something must have been created in the first second to give particles mass, but scientists haven't found it.
We have this hole. We have this missing piece. The centerpiece of this whole picture is what happened during that first second of creation. If you know that, then you can, quote, read the mind of God, as Albert Einstein used to say.
Mass is the very backbone of life.
If there were no mass, the universe would consist entirely of radiation, and nothing could bind together to form objects like you or I, or any of the things that appears to make the universe interesting. It would be a diffuse universe full of radiation, but very, very boring.
Discover how mass develops in the first second, and you uncover the root of life. If scientists can't find what gives particles their mass, that first second will remain an enigma. Our journey is almost finished, but a piece of the puzzle is missing, and it stumped scientists for decades. Then in 1964, at Britain's University of Edinburgh, physicist Peter Higgs comes up with a groundbreaking theory. He suggests an invisible force field sweeps across the universe in the first second, giving particles their mass. It's become known as the Higgs field. When particles interact with it, they gain mass.
For example, if I take a car and that's run out of gas and I push it on a road, eventually I can push it and I can move it along. But if it runs into the mud, if I try and push it, it will suddenly seem heavier. I can't push it as hard. It'll act as if it's heavier. Well, we think that particles have mass for a similar reason. There's this Higgs field, and some particles interact with it more strongly than others. And the particles that interacted with it less strongly are easier to push, and therefore behave as if they're lighter. The particles that interact with it more strongly are harder to move and act as if they're heavier.
Like mud, the Higgs field sticks to everything. When particles enter the field, they gain mass. The more contact with the field, the more mass they gain. Scientists believe the Higgs field is carried by its own special particle. Journalists call it the God particle. Scientists call it the Higgs boson. They think identifying this particle could reveal how we got here. The math is good, but no particle accelerator was powerful enough to find the Higgs boson. Until now. Deep beneath the countryside in Geneva, Switzerland, is mankind's most expensive experiment, the Large Hadron Collider, or LHC. The world's biggest particle accelerator and the best shot at finding the missing Higgs.
We've got to see if the Higgs particle really exists. And that's why we have to build these mammoth accelerators, to see if we can understand the mechanism responsible for the existence of everything we think of as solid and heavy in the universe today.
It cost $10 billion, took 14 years to build, and involves the work of 7,000 scientists. This year, they switch it on. On a small scale, it will recreate conditions last seen over 13.7 billion years ago. An explosion so powerful, it will echo the Big Bang itself. If it works, scientists like David Evans could solve the last mysteries of matter.
Because we're pushing the frontiers of science, we have to also push the frontiers of technology. It is, as well as probably the biggest machine in the world, it is certainly the most complex machine in the world.
Over 300 feet underground runs a 16-mile circular pipe. Inside, two beams of protons, thinner than a human hair, are accelerated to almost the speed of light, 186,000 miles per second. The LHC will smash particles together 7 times harder than any other accelerator. 300 trillion protons fly around the pipe in opposite directions and collide in the heart of enormous detectors. Lawrence Krauss inspects one of these detectors, each the size of a 5-story building.
Here we are at what's been aptly described as being one of the Gothic cathedrals of the 21st century. This monstrous structure made of thousands of tons of steel, more iron than in the Eiffel Tower, with tens of thousands of miles of wire. All of this designed by thousands of physicists from hundreds of countries, speaking dozens of different languages, with the precision of perhaps a millionth of an inch, just to detect what happens inside there.
The LHC uses 4 of these giant detectors along the beam pipe. The one they hope will find the Higgs is called Atlas. Atlas is half the length of a football field and weighs as much as a nuclear sub. It can detect 1 billion collisions per second. When the protons collide, the impact is so titanic, in a split second, it will recreate matter as it was just after the Big Bang. A shower of fundamental particles, like quarks. Somewhere in the debris, they hope to find the elusive Higgs. But finding one particle in this firestorm is like finding a speck of gold on a beach. The Higgs is so tiny and so short-lived, the detector won't see it directly. Instead, they hope to capture the trail it leaves behind, using the most high-tech cameras in the world.
When you look at a Skyrider, you see this gigantic plume of smoke, but where's the airplane? You never see the airplane. The airplane is too small to be seen. That's how we use detectors. Detectors cannot pick up the particle itself, but it can pick up the trail left over by the subatomic particle, and looking at the trail, we can determine what kind of particle it was and how fast it was moving.
The LHC will generate more data than any other instrument on the planet.
In a single second, the amount of information that's coming out of the collisions at the LHC that will be handled by these detectors is greater than the amount of information in all the libraries in all the countries in the world.
That data may hold the secret of mass, the missing piece in the universe's first second, and the doorway to the science of the future. To process all this information, the LHC uses the world's largest network of supercomputers. Even so, the search may take years to complete, but it's worth the wait. If it succeeds, the LHC could launch a new era in science. If it fails to find the Higgs and reveal how matter gets its mass, it will leave a hole in the riddle of the first second. New theories will have to be written, and more powerful experiments built.
Hey, I'm a realist. I realize that perhaps we'll find nothing. That could create a crisis in physics. It could stagnate all of physics if all of a sudden our machines are not powerful enough to unveil the next act, the next curtain, where we look at the next stage of matter and energy.
One thing they know, the LHC will take scientists closer to the Big Bang than ever before. It will reach back 13.7 billion years to recreate the very first second of the universe. The greatest second. Our cosmic clock takes its final beat of Planck time. The universe is 1 full second old. It's about 1,000 times the size of our solar system, and flooded with particles of matter, the raw material of everything around us. The universe is cool enough for the sea of quarks to bunch in threes, forming protons and neutrons. In the saga of the universe, this first chapter set the course of history.
The first second of the universe was an incredibly exciting and important time. During that first second, all the matter in the universe was made. All of the neutrons and protons were made. All the key components to make the universe today, we think, were already in place. And then everything just evolved forward.
In the next few minutes, the universe cools enough for protons and neutrons to form the first atomic nucleus. 300,000 years later, appears the first atom. In hundreds of millions of years, matter clumps to form the first stars. And in 1 billion years, galaxies like the Milky Way. More than 9 billion years after the Big Bang, Earth is born. One Big Bang, one single second. The genesis of everything.
By the time you've got to the end of 1 second, the rest of cosmic history is prescribed, including, ultimately, the future of the universe.
More than 12 billion years after the Big Bang, humans evolve. A species with the intellect to ask, how did we get here? And what is the universe made of? This year, science moves closer to discovering the answer. And the secret will lie in the first epic second. Stephen Hawking is the world's most famous scientist. He's on a quest to answer the biggest question of all. How did everything in the universe come to exist?
If we find the answer to that, we would know the mind of God.
Hawking's goal is to discover a blueprint for the universe. But he's locked in a battle with a disease that has left him paralyzed. And it's advancing. Can he unlock the secret of creation before his time runs out? Stephen Hawking is one of the greatest thinkers of all time. He's on a quest to understand the moment of creation when the universe is born. 20 years ago, he writes a book on the subject that becomes an international bestseller. It promises that soon he will have a single theory so powerful, it will explain all the mysteries in the cosmos. Why did the universe spring into life? And will it ever come to an end? A theory of everything.
We are getting close to answering the age-old questions. Why are we here? Where did we come from?
His determination to find answers has kept him alive far longer than any doctor predicted.
Stephen has got tremendous determination to solve the problems of the universe. And I think that's one of the key factors which has kept him going all these years.
But he lives his life on borrowed time.
The idea that my father had a very short lifespan was always present. I think it was there every single day.
Hawking will not rest until he unlocks the secret of how the universe came to be.
My goal is simple. It is a complete understanding of the universe, why it is as it is, and why it exists at all.
Born in 1942, Stephen Hawking has always been fascinated by the world around him. As a healthy child, he wonders what made the stars. By the time he's a teenager, he wants to find out where the entire universe came from. In the 1960s, scientists have yet to answer that question. Many believe our universe had no beginning. It is timeless and unchanging. But a new theory gains ground. Everything in our universe exploded from one tiny point, like a shower of fireworks. Scientists nickname it the Big Bang. But how can we suddenly go from nothing to everything in one moment of creation? Just 20 years old, Stephen Hawking's first mission is to find out. In 1962, he's just started his PhD at Cambridge University, where he's eager to prove himself. According to his old friend Kip Thorne,
Stephen was beginning to develop a reputation at that stage, but just barely beginning. And it was not at all obvious at that point that he was going to come to tower over all the rest of us.
But it's around this time that Hawking notices he's becoming very clumsy. A visit to the hospital leads to a startling diagnosis. Doctors discover he has amyotrophic lateral sclerosis, or ALS. The disease wastes his muscles. Before long, he will be completely paralyzed. Within 2 years, he will be dead. Hawking is just 21. His dream of unraveling the mysteries of the universe crashes down around him.
I had just been diagnosed with ALS, and I didn't know if I would live long enough to finish my doctorate.
It's the darkest period of his life. According to his daughter, Lucy Hawking,
he became very depressed and very saddened, He was casting around at the time for a PhD topic, but he didn't really see any point in going on, so I think everything seemed very bleak and very hopeless to him.
But then Hawking meets Lucy's mother, and they fall in love, despite his death sentence.
Getting engaged and getting married to her was for him the turning point, that was the event for him that turned him around and gave him hope and made him decide that he was going to carry on.
Hawking sets out to discover the origin of the universe before his time runs out.
Does the universe, in fact, have a beginning or an end? And if so, what are they like?
Scientists remain skeptical that something can come from nothing, as the Big Bang predicts. Hawking wants to find out. His first break comes in 1965. He attends a lecture by a brilliant mathematician named Roger Penrose. Hawking hears something that grabs his interest.
Stephen was in the audience at the back of the room, and he was asking some very pertinent and difficult questions.
Penrose suggests something astonishing. There's a hole in space where huge objects disappear. If matter disappears into nothing, maybe it can also appear from nothing. This could be Hawking's first step towards proving the Big Bang. But how can there be a hole in space? The answer might lie with gravity. Einstein's general theory of relativity says gravity isn't just a force of attraction, it actually bends space. Oxford University physicist Pedro Ferreira studies gravity's impact on the universe.
Well, Einstein realized that gravity wasn't this force that acted between two bodies. It was something much more elegant and beautiful.
Einstein pictures space and time as a fabric. Planets and stars press on this fabric and create dips. In a stroke of genius, he realizes gravity is not a force, but the bends in this fabric. The dips pull objects towards them.
Let's imagine this rubber sheet is space. These glass balls that I'm holding in my hand are planets and stars. Now, if you place a planet or a star in the universe on space, it'll create a dip. And the bigger the object you place, the bigger the dip. Imagine that the Earth is this coin, and I just send it coasting round our sun. It'll settle nicely into an orbit. It's just following the deformed nature of the fabric of space. That's what gravity is, and that's what Einstein realized.
So what we experience as gravity is actually the curve of space-time around us.
The theory of relativity does force us to fundamentally change our ideas of space and time.
When that fabric gets stretched to breaking point, something dramatic happens. A hole in space opens up. A hole down which things can disappear. This chain of events starts when a star dies. It begins to collapse in on itself, getting smaller and denser. If a star 20 times the size of the Sun dies, it has a drastic effect on the fabric of space-time.
If you imagine what this means in terms of the fabric of space-time, you're just pressing down on it incredibly hard. You're pressing so hard on it that at that point, it almost tears.
The depression is so deep that nothing can climb out, not even light. This is known as a black hole.
If this star is big enough, it'll collapse to a tiny, minute point, incredibly dense. And it'll create a dip in space, so deep that if an object tries to pass by, it'll be sucked in, it'll be sucked all the way down into that point. That's a black hole.
Roger Penrose discovers that at the center of a black hole is a point of pure gravity. It's called a singularity.
As you go into a black hole, you will encounter something which goes against the laws of physics as we previously understood it. Roughly speaking, you could say a singularity is where space and time come to an end.
A singularity is like a drain, a hole in space. Everything that falls down it disappears. Hawking wonders if the opposite could be true. According to the Big Bang Theory, all the universe suddenly sprang from a point of nothing. Could this hole be the key to explain how this happened? In a moment of genius, he sees the solution. It's elegantly simple.
I soon realized that if one reversed the direction of time in Penrose's theorem, the collapse became an expansion.
Instead of sucking everything in, a reverse black hole explodes out in a shower of space, matter, and time. Exactly as the Big Bang Theory predicts. Against a sea of skepticism, Hawking proves the universe suddenly appeared from nothing. It sprang from inside a singularity. The debate is over.
The universe must have had a beginning in time. This was finally proved by Penrose and myself, on the basis of Einstein's theory of relativity.
Hawking found the origin of time, but he hasn't found a way to stop it ticking. He's now 26 years old. His disease has advanced up the muscles in his legs. He can no longer walk. But his brain is alive with questions. Hawking now knows a moment of creation happened, but not what caused it to explode into being. This will prove his biggest challenge yet. Can he find the answer before his body collapses? Stephen Hawking has discovered where the universe began. A tiny hole in space, known as a singularity. This exploded in a Big Bang to create everything in the universe. But he doesn't understand what made it explode.
Why are we here? Where did we come from?
To find the origin of the universe, Hawking used Einstein's general theory of relativity. Relativity explains how gravity acts on large objects like stars and planets. But when the universe was born, it was smaller than an atom. So to understand how it grew, he needs the theory of the very small. Quantum mechanics. The trouble is atoms are unpredictable. They don't follow the ordered rules of gravity. The theories of general relativity and quantum mechanics are incompatible.
Unfortunately, these two theories are known to be inconsistent with each other. They cannot both be correct.
At NASA Goddard Space Flight Center, Kim Weaver is interested in the conflict between the theories.
In a way, this ball can be used to represent the tension or the battle, actually, that's going on between general relativity and quantum mechanics, quantum physics. The surface is smooth. It represents a large scale. General relativity, gravity, acts on a very large scale. And we can predict what's going to happen based on those equations. But if we zoom into the quantum world, things are very chaotic, and these larger scale laws don't apply.
We used to think that electrons orbited around the nucleus of an atom like planets around the sun. But scientists now know that electrons pop up and disappear at random. They can even be in more than one place at the same time. Normally, gravity appears to play no part in this chaotic world. But at the moment of the Big Bang, there was a huge amount of matter held together in a tiny space. So gravity must have had a role.
Bringing these two ideas of general relativity and quantum mechanics together into a unified whole is what Stephen Hawking set out to do.
He wants to combine the two theories into a theory of everything in order to find out what triggered the moment of creation.
If we find the answer to that, it would be the ultimate triumph of human reason.
Hawking knows the theories of gravity and quantum mechanics clash at the instant of the Big Bang. But he believes they also clash inside a black hole. This is where a huge amount of matter crushes to a tiny point. So he returns to black holes to investigate. If he can unite the two theories here, it could help him understand the Big Bang. Relativity says nothing can exist on the edge of a black hole. Everything is sucked in. But quantum mechanics states that space is never empty. It's full of tiny pairs of particles.
Space is essentially empty to us, and it is empty when we look at it. It appears to be empty. But at this very tiny level, it's not at all. In fact, it's filled with virtual particles coming into existence and annihilating each other all the time.
Energy waves in space create tiny particles. Every particle has an antiparticle. One has positive energy and the other has negative energy. These pairs appear, but then collide and destroy each other.
Quantum mechanics was very well established, but no one knew how it played into the larger scale of the universe. And that's where Stephen took those two things and said, let me now play with this in my mind. How does this work? If I put a virtual pair next to a black hole, what happens?
To unlock the secrets of a black hole, Hawking must discover what happens to these particles. Now 28, his body is wasting away, but his mind doesn't let him down. He has a flash of inspiration. The answer lies with the fact that the particles are positive and negative.
And what Hawking realized, what's really fascinating about this, is when a pair of particles like this appears near the event horizon of a black hole, the one with negative energy falls into the black hole, and the one with positive energy escapes as radiation.
The negative particle is pulled into the black hole, but the positive particle has just enough energy to avoid getting sucked in. It's released as a particle of radiation. Hawking has proved black holes give off heat, and these positive energy particles are the source. It's called Hawking radiation. The revelation that something can escape the grip of a black hole shocks the world.
When I first announced the results of my calculations, I was greeted with incredulity. By their definition, black holes are not supposed to emit anything.
Hawking proves that while gravity sucks in the negative particle, quantum mechanics allows the positive particle to escape. The two theories can work together. It's the closest anyone's ever come to a theory of everything. But while the world celebrates Hawking's discovery, privately he is concerned. His theory of everything has a fatal flaw. Stephen Hawking is on a quest to unite the two opposing sides of modern science: general relativity and quantum mechanics. If he achieves it, he will have a theory of everything. One equation that could reveal the underlying plan of the universe. It might even explain how it exploded into being. To find it, Hawking needs to piece back together an explosion that detonated 14 billion years ago, the Big Bang. But how? His starting point is an astonishing prediction. Black holes explode, and in a way that makes them very similar to the Big Bang. Hawking discovered that unlike negative particles, positive particles can escape the gravity of a black hole. Now he takes his theory a step further and discovers that over time, a black hole begins to evaporate like a puddle in the hot sun. Over billions of years, it sizzles away. As it gets smaller, it gives off more radiation. It shrinks faster and faster until it shrivels right out of existence. And at that moment, something dramatic happens.
The most reasonable guess is that it would disappear completely in a tremendous final burst of emission, equivalent to the explosion of millions of H-bombs.
It's this tremendous explosion from a tiny point that grabs Hawking's interest.
The Big Bang resembles a black hole explosion, but on a vastly larger scale.
So Hawking's question is, could anything come out of the black hole when it explodes? If it is similar to the Big Bang, will it release a high-energy stew of particles, like in the early universe?
An understanding of how black holes create particles will lead to a similar understanding of how the Big Bang created everything in the universe.
It could be a mini version of the moment of creation. But all of this is theoretical. No one knows if black holes do explode. Now, for the first time, we may actually see this happening. On June 11th, 2008, NASA launches a state-of-the-art telescope called Fermi. The telescope will search the vast expanse of space for the last gasp of a tiny black hole. As it dies, it should release a huge blast of high-energy particles called gamma rays. That's what Fermi should see. Steve Ritz is the lead scientist.
What we'd be searching for is a tiny object, a microscopic object, no bigger than an individual proton, the core of a nucleus, and yet it's shining apparently like one of the brightest objects in the whole sky.
But Fermi's search for these black holes isn't easy. There's a flood of gamma rays from exploding stars that could mask an exploding black hole.
So here's what the whole sky would look like if you had gamma ray eyes. We'd hope to see the individual black hole at the very end of its lifetime making an explosion. And that could happen really anywhere on this image. And that's why it's so incredibly interesting, because one of those contributions could be the individual primordial black holes producing their Hawking radiation.
Ritz's team continues to search for a black hole explosion caused by Hawking radiation. These events are rare, but the payoff is huge, so the search continues.
It would be incredibly exciting if we discovered a family of gamma ray bursts that had no other explanation than the Hawking radiation from microscopic black holes. It would be a revolution in science.
While Fermi searches for clues to how the universe kick-started into life, Hawking's uncovered a mystery that could derail his quest for a theory of everything. In the moment after the Big Bang, something strange happens to gravity. For some reason, it suddenly changes gear and gets weaker. And this is crucial to our existence today. If gravity hadn't weakened, it would have yanked all matter back in on itself. And the universe we know today wouldn't exist. The mystery is, why did gravity weaken just enough to stop the universe from recollapsing? Hawking needs to find a way to explain this.
If we want to know what happened when the universe began, we have to have a theory to explain gravity on a very small scale.
Gravity is actually the least understood force in nature. It's much weaker than the other forces. Consider electromagnetism, for instance. Electromagnetism is the force that tears up our skies in violent storms. It also binds atoms together into everything we see around us. At the instant of the Big Bang, scientists think electromagnetism and gravity are the same strength. As the universe expands, gravity dramatically weakens. Sean Carroll is a cosmologist who studies gravity at the moment of the Big Bang.
Gravity is something we notice every day. We drop things. We have to work against it to climb a set of stairs or to move around. It seems to us like a powerful, important force in our lives. So the puzzle is that, in fact, gravity isn't really as strong as we think. I can take something very, very tiny, like a set of keys, and if I drop it, it could smash something far below. Nevertheless, something as small as this magnet can be more powerful than gravity just because the electrical and magnetic forces here are intrinsically more powerful. Just a tiny little magnet is able to overcome the gravitational force exerted by the entire Earth.
Nobody knows why after the Big Bang, gravity changed gear and became weaker. Hawking's theory of everything should reveal the inner workings of the universe, but it can't explain this. Something is wrong with the blueprint. He sets to work trying to puzzle it out. He now has the top minds in the field working with him. But only a few members of this inner circle can understand his speech. He must painstakingly dictate his scientific papers. The process is slow, but he is making progress. His family worry he is pushing himself too hard.
There was always this terrible, terrible fear whenever anything went wrong, or when he started choking or coughing, or he got an infection, that this was it. Because you just never knew what might happen next.
Then in 1985, on a trip to Geneva, Switzerland, tragedy strikes. Age 44, Hawking collapses with pneumonia. An emergency tracheotomy saves his life, but severs his vocal cords. Unable to communicate, completely cut off from the world, Hawking plunges into his own black hole. 6,000 miles away in Lancaster, California, speech software designer Walt Wolters gets an urgent call from a friend about a new client.
He mentioned that he was a physics professor at Cambridge. I said, gee, that sounds like Stephen Hawking, you know, and he said, well, I'm not allowed to say. And I said, well, I'll tell you what, if it is, I'll donate whatever he needs.
Hawking is able to make a slight movement with his fingers, so he can use a switch. Wolters designs an ingenious system that helps predict the words Hawking will use.
I choose the letter B, and I'm going to choose the word black here. Now, after I selected the word black, and in Stephen's case, the word black is almost always going to be followed by the word hole. Now if I want to speak that, I can just choose the speak command here.
Black hole radiation.
Waltos sends the machine to Hawking, and the voice we hear today is born.
I like my present voice, even though it has an American accent.
It's the breakthrough Hawking needs to carry on with his work.
The first time I came back to see him after the initial time, he was scanning at 10 steps per second. This is blinding speed.
He'd sort of risen like the phoenix from the ashes to be this new character with an American electronic voice. And he was so sort of good-humoured about it that you just felt admiration, I suppose.
Never in these circumstances have I ever seen him show frustration. He just keeps going at it.
Hawking returns to Cambridge and click by click presses on with his work. He employs a team of graduate students to help with the computations.
I'm going to talk about...
He's been given another shot at cracking the theory of everything. And he's more determined than ever. Stephen Hawking has spent 3 decades trying to discover a theory of everything. A powerful set of laws that governs the entire universe. From the tiniest particle to the largest galaxy. It's been the holy grail of theoretical physics for over a century. Hawking painstakingly lays the groundwork for this theory. But he could be beaten to the finish line by a radical new theory, string theory. One of its architects is physicist Michael Green.
It represents such a profound change in our way of thinking of the universe, both in the very small and in the very large, that it should have all sorts of repercussions.
String theory could even be a candidate for the theory of everything. It unifies every single thing in the universe, from atoms to stars, planets to people, because they are all made from one ingredient, strings. Strings are so tiny, there's no way to see them directly. Equations show they could be a trillionth the size of an atom. To get an idea of how small this is, imagine an atom blown up to the size of our solar system. The nucleus would be the size of our sun. But even in this scaled-up world, strings are tiny, smaller than the Earth, smaller than the smallest state, about as tiny as one person in our entire solar system.
I would be the size of a string.
Strings are the building blocks of everything we see around us. The entire universe is a gigantic mesh of these vibrating strings.
We're all made of string, and we're moving in a stringy space-time, and everything is stringy.
To correctly describe our universe with string theory requires something incredible. The world we see around us is made up of 3 spatial dimensions: width, height, and length. But Green and his colleagues think that we are actually surrounded by at least 9 dimensions. This may sound like science fiction, but Green suspects these extra dimensions are hidden from our view.
Clearly, since we don't see these extra dimensions in everyday life, they must, in some sense, be very small and not directly observable.
Green collaborated on his theory with Caltech physicist John Schwartz.
We have the perception that we live in this 3-dimensional world, even though it may in fact be more dimensions.
But how can there be dimensions that we haven't noticed?
This is a line, which is a 1-dimensional object. But if we turn it around and look inside, we can see that it's actually a rolled up piece of paper, which is a 3-dimensional world. We can see that there's an inside, and if we put an ant in here, the ant can go around in 3 directions. So the ant sees it as a 3-dimensional world.
The extra dimensions reveal themselves if, like this ant, you're small enough to see them. Schwartz believes these extra dimensions are curled in on themselves, curled up into tiny knots that are so small we can't see them.
But the fact that we don't see them doesn't mean that they don't have a profound effect on the universe we live in.
Schwartz and Green believe these extra dimensions explain why gravity is so weak. They believe at the moment of the Big Bang, gravity is strong, but then the universe expands. Gravity spreads out into the extra dimensions, weakening as it goes. This explanation removes the final stumbling block to the theory of everything.
Let's consider an analogy in which gravity is like music. When I'm close, it's loud, and as I walk away, it gets quieter.
The music disperses in different directions. As it does so, it weakens.
Here, the music is almost inaudible, and that's because it's spread out over space. Now imagine, instead of music, that we're talking about gravity, and imagine that there are extra dimensions in space. Extra dimensions in which the gravity can spread out even more.
More dimensions in space mean more directions to spread across. This in turn makes gravity even weaker. String theory explains how the universe we see today exists. After the Big Bang, as the universe expands, gravity spreads out through these tiny extra dimensions and weakens. Gravity weakening is what stops the universe from collapsing back in on itself. It's the missing piece in Stephen Hawking's quest for the theory of everything. He concedes that Green's string theory is the best contender to explain how the universe came to be.
Stephen Hawking's relation to string theory is very intriguing. I think he's a big admirer, but not necessarily a believer. His ideas have had a profound influence, actually, on many things that have happened in string theory. And with a bit of luck, string theory has had some influence on his ideas as well.
We believe that there is one fundamental theory that describes dimensions that are curled up so small that we don't notice them. Nevertheless, these hidden dimensions affect physical quantities like gravity.
One hitch is that none of this has ever been proved. String theory and the extra dimensions exist only on paper. Like so many of Hawking's own discoveries, there is no proof. But that might be about to change. And the earliest moments of the universe could soon be revealed. This is the CERN laboratory in Geneva, Switzerland, home of the Large Hadron Collider, the biggest experiment ever built. Deep below ground, scientists are attempting to recreate the conditions that existed just after the Big Bang, to reveal how everything around us came into being. Scientists will search for clues to what happens in a high-energy environment, like the one that followed the instant of creation. It's the moment Stephen Hawking has been waiting for.
Why is the universe the way it is? A new window on the very early universe will be opened.
Scientists will fire subatomic particles in opposite directions. The particles will travel for almost 17 miles, accelerating to close to the speed of light. Then they will slam into each other with a force trillions of times more powerful than dynamite. This high-energy collision will produce particles similar to those in the aftermath of the Big Bang. It should reveal the key ingredients of the universe, and possibly the recipe behind them. The Large Hadron Collider will take us as close as humanly possible to the moment of creation. And in an incredible one-two punch, it could prove that both string theory and Stephen Hawking are right. String theory predicts that we are surrounded by tiny extra dimensions. These extra dimensions trap gravity. If this is true, particles colliding in a small region could feel ultra-strong gravity. This could trigger matter to collapse on itself into a mini black hole, exactly as Hawking predicts. So rather than a Big Bang machine, the collider could become a black hole factory.
The black hole might actually grow because over time, the black hole will pull material into itself. It could grab onto molecules in the atmosphere. So its mass will increase. I have no idea what will really happen in that case, but that means that the experiment does need to be controlled well.
Researchers estimate it's theoretically possible. They could create mini black holes at the rate of 1 per second. Some people fear that just one black hole could swallow the Earth. It's a terrifying thought. Scientists at CERN, however, are putting their faith in Stephen Hawking. Hawking predicts that small black holes will evaporate. They should burn up almost instantly, lighting up like a Christmas tree.
They will produce little black holes, which will then radiate and decay and disappear, according to Stephen Hawking predicted many, many years ago. And that would be, of course, truly exciting.
If black holes do appear, it will reveal the secret of why gravity weakens after the Big Bang. Tiny extra dimensions in space.
If they found proof of extra dimensions, I would be completely staggered. It would be extraordinary, because we would have finally found that space had more than 3 dimensions, which is fundamental.
A fault in the complex machinery delays the big startup until spring 2009. Even then, it may take years to comb through the data for proof of extra dimensions and tiny black holes. After searching for a theory of everything for almost half a century, Hawking desperately wants to live to see the culmination of his life's work. So once again, he faces a battle against time.
There are grounds for cautious optimism that we may now be near the end of the search for the ultimate laws of nature, though much more work will be needed.
Stephen Hawking is nothing if not a fighter. He has taken on the biggest mysteries in the universe and cracked them. He found the birthplace of the universe. He forced the two opposing sides of modern science together to prove that it is possible to escape a black hole. An achievement he has mirrored in the battle with his disease.
The greatest thing I've learned from my dad is if you fall into a black hole, don't give up, you can get out of it again. And that's so clearly what he's done with his life.
Hawking has outlived his death sentence by over 40 years to become one of the longest surviving sufferers of amyotrophic lateral sclerosis in the world. But questions remain, and a single equation powerful enough to describe all of existence still eludes him.
Stephen's grit, his stubbornness, have contributed to his continuing vigorously ever so much longer than anybody ever expected. And I'm hopeful that he may still be around working on this 20 years from now.
Stephen Hawking is as determined as ever to find a definitive theory of everything for our universe.
65 million years ago, a 1,000 billion ton asteroid smashes into the Earth, wiping out the dinosaurs. Massive impact events are likely to happen once every 75 million years. Today, scientists scan the skies for these giant killers. But an asteroid just 150 feet across could devastate a city the size of New York. Asteroids this size could hit any time. And right now, there is nothing we can do to stop them. It's a nightmare scenario. 1,000 billion tons of rock on a collision course with Earth, hurtling towards it at over 50,000 miles per hour. It hits with the force of 300 million nuclear weapons. Enough energy to wipe out every human being on the planet. This is no nightmare. It's real. 65 million years ago, a rock this size smashes into the Earth. And wipes dinosaurs from the face of the planet. It could be 10 million years before the next impact this big. But smaller asteroid impacts can also be devastating, and they happen far more often. Around 50,000 years ago, an asteroid slams into the Arizona desert, hurling 175 million tons of rock into the air. Meteor Crater is nearly a mile wide and 570 feet deep. Amazingly, the Canyon Diablo asteroid that created it was only 130 feet in diameter, about the size of a small jet plane. There are more small asteroids like this in space than large ones, and they can hit the Earth as often as every few hundred years. One scientist at Northern Arizona University thinks Meteor Crater has a message. Professor Ted Bunch.
Events like this, smaller events, they could happen anytime.
And they're capable of massive destruction. The extreme heat of this blast tore through the desert sandstone.
This is coconino sandstone, and it's in pretty good shape. And there's a piece here. This is also coconino sandstone that is severely shocked. Probably temperatures exceeding maybe 3,000 degrees Fahrenheit. Huge amount of pressures, and you can see the difference. This used to be this.
Imagine the same thing happening today. What would a 130-foot wide object like this do to New York City?
If this meteorite had hit Manhattan yesterday, about 80% of the people would have had serious injury or died. All the boroughs of New York would have been affected, either by the heat, the shock wave, the seismic activity, crumbling of buildings, and collapse.
Everything within a 5-mile radius would be obliterated. Asteroids have crashed into our planet ever since its formation. The key to their destructive powers lies in their mass and the speed of impact. As an asteroid hurtles towards Earth, it builds up huge amounts of kinetic energy, much like this speeding car. The faster the car goes, the greater the kinetic energy, even though the car's mass stays the same. When the speeding car hits a brick wall, it doesn't inertly stop. All the kinetic energy is converted into an explosive force. The crash generates heat metal bends, plastic and glass shatter. An asteroid behaves exactly the same way when it impacts the Earth. Only because it's traveling at 50,000 miles per hour, the explosion is far greater. Here in Arizona, evidence of the impact stretches 6 miles from the crater's edge. Pulverized rock particles called impactites shot across the landscape at deadly speeds.
We have impactites, all these little dark guys. Those are melt rocks. There's literally tens of thousands of them right in this particular area. These were ejected as far as 3 to 5 miles under very high velocities, 2 or 3 times the speed of a rifle bullet. But if you were an animal in this area and you had thousands of these particles coming at you, you'd be toast.
Impactites are a major clue to an asteroid strike and can reveal previously unknown impacts. Fossil hunters in Alaska uncover fragments of tusk from woolly mammoths. They are peppered with buckshot-like particles and date back 34,000 years to a time when the number of large mammals in the region inexplicably dropped. Have fossil hunters uncovered evidence of an undocumented asteroid impact? Dr. Richard Firestone searches for evidence.
We analyzed several of the particles from various tusks, and they had the unique signatures of meteorites. They were rich in iron and nickel, which is a critical component of most meteorites.
This is strong evidence that these woolly mammoths died from an asteroid impact. The force of blast was devastating.
We did an experiment with a shotgun to see what would happen if you shot a mammoth tusk, and they simply bounce off the outside. Nowhere near enough energy for that.
A shotgun fires at 600 miles an hour. Asteroid fragments travel over 30,000 times faster.
In order for the impact particles to penetrate the tusks as they did, they'd have to have been moving at tens of miles per second.
Firestone's mammoth died in an asteroid impact 34,000 years ago. The impactites embedded in the mammoth tusks prove that previously unknown asteroids have struck the Earth. And new evidence reveals that they didn't just kill mammoths. Humans died too. 13,000 years ago, North America is locked in an ice age. Large mammals like giant sloths and woolly mammoths roam the land. The nomadic Clovis people live alongside them. Then the fossil record stops. Many species of mega mammal abruptly disappear. What causes this sudden, mysterious disappearance? The Clovis culture also vanishes from the archaeological record. Is it starvation? Disease? No one knows for sure. Now a cave in northern Ohio may hold the answer. 30 feet underground, an archaeologist from the University of Cincinnati discovers evidence of an ancient catastrophe. Ken Tankersley and his team dig up a layer of burnt material in the soil. It dates to when the Clovis and the mammoths vanished. To archaeologists, this distinctive carbon-rich layer, called the black mat, indicates intense burning, a sure sign of a destructive event.
Beneath this layer, we have evidence of large mega mammals. Above it, there's none whatsoever. This mat was deposited in a very quick and sudden event. Beneath it, you have evidence of Clovis people. Above it, you have absolutely none. The real mystery is what happened at this very time.
What catastrophe caused this black mat? Tankersley searches inside the black mat and uncovers the bone of a wild pig, known as a peccary. It tells a disturbing story.
This particular bone has not seen air in 13,000 years.
the bone shows signs of extreme burning.
We know this burning is not the result of cooking. These animals were larger than I am, and to take a human body and a natural fire, you have to burn the body for days. This type of burning clearly came from a very intense, very fast burning, a single event fire, if you will.
Did an asteroid cause this deadly blast of heat? If it did, there is a vital piece of the puzzle missing. There's no evidence of a crater. This leads to a disturbing possibility. Could an asteroid be big enough to destroy an entire culture, yet so small it leaves no trace? Around 50,000 years ago, a small 130-foot wide asteroid smashes into the desert of Arizona and creates Meteor Crater. An impact this size could wipe out a major city. But this isn't the last time Earth was hit by a small but deadly asteroid. We're realizing that Earth is far more vulnerable than we once imagined. And some devastating impacts have left almost no trace. Archaeologist Ken Tankersley has found a black mat, evidence of an extreme heat event in a layer of rock dating back 13,000 years. The same time that the Clovis culture, one of the earliest in North America, abruptly and mysteriously vanished. Is an asteroid responsible? New research at sites across the United States also uncovers the black mat layer of burnt material, all dating back to the same time. The chemical analysis is compelling, but Tankersley wants to be even more certain. He returns to the Sheridan Caves in Ohio to take further samples. At the University of Cincinnati, an electron microscope takes a close-up view. Tankersley magnifies the tiny sample 10,000 times. He spots compelling evidence of a devastating asteroid impact. Detonation diamonds.
What's kind of tantalizing here is the possibility that these are associated with a cosmic event, if you will. Detonation diamonds are the result of a strong impact from either a large meteorite, an asteroid, or a slice of comet.
Major asteroid impacts have shaped history more dramatically than ever imagined. It seems increasingly likely that an asteroid is the reason for the Clovis culture's disappearance 13,000 years ago.
In geological time, 13,000 years ago is yesterday. The implications for us living on the planet today, we always think it's not going to happen to us. The reality is when it's going to happen next.
No one has ever found a crater from this event. So the question is, how big was the asteroid that caused this catastrophe? Asteroids are mostly composed of rock and metal, debris left over from the formation of the solar system 4.5 billion years ago. Thousands of these objects orbit near the Earth, some as big as mountains, others smaller than a speck of dust. The size of the asteroid that may have ended the Clovis culture is a mystery. One scientist thinks he can find the answer. Professor Peter Schultz of Brown University starts with one vital piece of information. The Clovis culture ended during an ice age. 13,000 years ago, North America is partially covered in a layer of ice up to a mile thick, the Laurentide Glacier. So the question is, what happens when an asteroid slams into ice rather than land? Schultz suspects the asteroid would leave a crater in the ice, a crater that might eventually melt, hiding all evidence of the impact.
The fact is, ice was there, and there's no reason why an impact couldn't hit there as well as any other place.
Schultz tests his theory in the vertical gun range at NASA Ames Research Center outside San Francisco. The vertical gun is unique. It can fire projectiles at 13,000 miles per hour, equivalent to the speed of a real asteroid. Schultz must find the exact ratio of asteroid size to ice thickness to cause a devastating explosion, but leave no crater. He uses a tiny glass bead in place of an asteroid and a half-inch sheet of ice for a mile-thick glacier. The experiment will tell Schultz how much damage a half-mile wide asteroid would cause.
We got about 3/4 of an inch of sand in there. We're going to be firing a projectile about 1/4 inch across, but the question is whether or not it's going to penetrate all the way through.
An asteroid colliding with Earth smashes into the atmosphere. Friction superheats it as it plummets through the air. Schultz simulates Earth's atmosphere by filling the chamber with argon gas. The gun will fire the projectile at almost 4 miles per second, the equivalent speed of most asteroids.
Every time you do an experiment, you learn something brand new. I love surprises, and invariably we have a surprise.
Could an asteroid be small enough to leave no crater, but big enough to devastate large parts of North America? It's a pressing question. The solar system is full of smaller asteroids. During the last ice age 13,000 years ago, an asteroid may have incinerated parts of North America, but left no crater. Scientists are trying to find out how an asteroid could be big enough to wipe out an entire culture and yet leave no imprint. Peter Schultz uses the vertical gun range to test what happens when a half-mile wide asteroid hits a mile-thick sheet of ice.
Oh! Pow! Oh my gosh! That's gotta hurt. Did you see that? Look at that stuff. Man, that hurt.
A glass bead enters the chamber at 13,000 miles per hour. When it hits the gas simulating our atmosphere, it burns and then explodes. A fireball smashes across the ice.
This is when you say, oh crap. It's coming for you. You can't even hear it because it's going faster than the speed of sound.
The experiment shows that a half-mile wide asteroid hitting a mile-thick ice sheet would have catastrophic consequences.
Oh, wow. There's no crater. You don't even know that it happened. Let me go ahead and take some pieces out, okay? Here's where one big mass hit. You see the little pit in there. If the ice hadn't been here, we would have formed a crater about that big. The ice acted like a flak jacket. You know, once this goes away, once the water goes away, you can't tell that anything was here. That's remarkable.
The after effects of the impact would have been felt as far away as Europe. But the asteroid itself leaves no crater.
All you need is an object about a half-mile impacting into that. It might have formed a crater 20 miles across, but when the ice disappeared, melted, went away, you might completely remove the evidence. It's kind of like a perfect cosmic crime.
The asteroid that may have ended the Clovis culture could have been just half a mile in diameter. An estimated 1,000 asteroids of around this size hover near to Earth at this very moment. Scientists decide to look at other more recent impacts in order to reevaluate their size. One of the most famous and powerful recent asteroid impacts is known as the Tunguska event. June 30th, 1908, an asteroid explodes over Tunguska, Siberia with the force of 1,000 atom bombs. Tunguska is so remote that it takes 19 years for scientists to mount an expedition to examine it. The team brings survey equipment to record the devastation. The blast tore 60 million trees out of the ground. 800 square miles of Siberia, an area 1.5 times the size of Oklahoma City, are flattened and scorched. There is no crater. The asteroid exploded before it hit the ground. The size of the asteroid remains a mystery for almost 20 years. Then in the 1950s and 60s, impact specialists attempt to simulate the strike using data from nuclear tests. Some scientists estimate the Tunguska asteroid was up to 600 feet across. That estimate has been reduced to around 200 feet. In 2007, Dr. Mark Boslow reanalyzes the data using a supercomputer. He thinks the asteroid is much smaller.
Most of us had been thinking that it was an asteroid, came streaking in, it got down to about 5 miles above the surface and exploded with an energy of between 10 and 20 megatons. So we knew roughly what the wind speeds and what the thermal effects would be on the ground for an explosion at that height and that magnitude. And what was observed at Tunguska was consistent with that.
But this theory assumes a nuclear weapon and an asteroid impact in the same way. A nuclear weapon explodes from a single static point. But an asteroid is different. It's moving fast. So when it explodes, the energy it releases keeps moving, causing even more destruction.
When it explodes, it vaporizes, it begins to expand. It's very much like a nuclear explosion, except it's got a lot of mass and it just keeps on moving.
So the explosion over Tunguska spread out across the landscape.
We realized that even though it explodes at this high altitude, that explosion continues downward. All that hot rock, all that vaporized asteroid material continues downward, and finally it slows down and finally stops a few miles above the surface. The blue color here represents the shock wave, that blast wave that carries mechanical energy down. So that's very high wind speeds, hurricane force wind speeds. So when that hits the ground and sweeps across the ground, that's blowing trees down.
The old model assumed a stationary explosion. That meant a 200-foot asteroid. The model was probably wrong. A moving object could be small and still cause that much devastation.
The Tunguska event could have been caused by an asteroid as small as 100 feet in diameter.
Boslow's findings sent shockwaves through the scientific community.
There are many more smaller asteroids in Earth-crossing orbits than there are larger asteroids. Therefore, if Tunguska was from a smaller asteroid, a Tunguska-like event is more frequent than we had previously thought.
Scientists once thought an asteroid around 600 foot wide caused the obliteration of Tunguska. A rock that big hits Earth once every few thousand years. Now they've downgraded the size of the Tunguska asteroid to just 100 foot across. These hit on average every few hundred years, and the last one we know of was in 1908.
The most likely scenario for a big destructive impact event is from a Tunguska-sized object.
It's a game of chance. Another Tunguska-sized asteroid might not strike for another 100 years, or it might strike tomorrow. Luckily, the Tunguska asteroid hit in an unpopulated area. In today's world, we might not be so fortunate. The question is, what can we do to protect ourselves from asteroids, big or small? In 1998, the US Congress instructs NASA to take action. It sets up the Space Guard Survey to identify and track any near-Earth asteroids that pose a threat to our planet. The first step is to identify the asteroids at least 3,000 feet across, the ones big enough to cause massive destruction if they ever hit Earth. So far, 1,100 asteroids this size have been located. The Catalina Stewart Observatory at the University of Arizona is part of this SpaceGuard network. Asteroid hunter Ed Bayshore and his team comb the skies for these giant asteroids.
Essentially what we need to do is we need to image an area on the sky 4 times over the course of about 40 minutes.
The computer takes 4 telescope images of the same patch of night sky. The stars stay still. But near Earth objects, the asteroids, move through frame.
So for instance, here's the first image of a field that we just observed. There's the second image, there's the third, and there's the fourth. When we start it blinking, we can see that we have an object right here in the field. As it turns out, that is probably an NEO by the way it's moving.
But what about the smaller asteroids? The ones we think wiped out the Clovis culture or exploded over Tunguska. Right now, Bayshore doesn't search for them at all.
There's many more objects that are smaller. And just because they're smaller doesn't make them not dangerous. In fact, we think the objects around 300 feet in diameter and larger, which are much more numerous, may actually represent a considerable threat.
Now space scientists are determined to track these smaller asteroids. Among them is a man who is no stranger to the hazards of outer space, former Apollo test pilot Rusty Schweikert.
Now, it's very important that we start looking for these smaller ones because they hit with much higher frequency. From 100 to 150 feet in diameter and larger, we can start having serious effects on the ground. They are huge in terms of natural disasters.
The smaller the asteroid, the harder they are to find. They move at around 50,000 miles per hour in orbits that are extremely hard to track.
Because we've only been looking for the biggest ones up until this time, our telescopes really aren't adequate to give us the information, the early warning that we need on the smaller objects.
Tracking small asteroids requires specialized telescopes. These are still years away from completion. But occasionally, astronomers get lucky. In 2004, they pick up a moving object in the sky. Closer inspection reveals it's an asteroid, and it's 900 foot across. Researchers name it Apophis, after the Egyptian god of evil and destruction. It is big enough to destroy an area almost the size of Texas, and it is coming our way. In 2004, at the Kitt Peak Observatory, Arizona, scientists spot a new and relatively small asteroid. It looks like it is on a collision course with Earth. It is called Apophis, and it's 900 feet across. Around 10 times the size of the asteroid that created Meteor Crater in Arizona. At the Massachusetts Institute of Technology, Dr. Richard Binzel tracks its trajectory.
An impact the size of Apophis in terms of the immediate damage would be regional, roughly the size of France in terms of its immediate catastrophic effects.
Based on initial observations, researchers believe it has a relatively high chance of hitting Earth in 2029. The asteroid poses a real threat. Binzel needs to discover what Apophis is made of. He studies the asteroid via a remote link to a telescope in the Mauna Kea Observatory, Hawaii.
The instrument we're using is a spectrometer. The different minerals that are present in asteroids have very critical absorption bands, or very fingerprints, if you will, in these wavelengths of light that let us distinguish between different kinds of compositions, different kinds of minerals.
No two asteroids are the same. Most are solid, but some are loose piles of rubble. The majority are made of rock, but some are composed of metals and other materials. Apophis turns out to be mostly made of chondrite, a type of rock.
We think that Apophis is like this type of meteorite. It's an LL chondrite meteorite, And the beauty is that we can measure the properties of this meteorite in the laboratory. And if we scale this meteorite up to the size of Apophis, which we think is about 900 feet across, the mass of Apophis is about 20 million tons. The energy that it would have if it hit the Earth is about 375 megatons, the kind of energy we usually talk about with nuclear arsenals. And that's more than 20,000 times the energy of the blast at Hiroshima.
With the asteroid's speed and orbit mapped, researchers can predict its trajectory more accurately. New data suggests that the 900-foot asteroid is headed this way in 2029. It will miss Earth by just 18,000 miles. A near miss in astronomical terms. But if Apophis had been on a collision course, what could we have done? The most obvious solution is a nuclear bomb. The theory is that a blast could shatter it into pieces. But this approach is risky. The blast fragments could continue on a collision course with Earth. And to make matters worse, they are now radioactive. Instead of eliminating the risk, a nuclear explosion could increase it. Earth could get hit by a cosmic shotgun blast, resulting in even more widespread devastation. One scientist alarmed by this scenario is Dr. Massimiliano Vasile of the University of Glasgow in Scotland.
What could happen is that the shock wave due to the explosion of the outer crust fragment the asteroid. So it might be that basically we have not just one asteroid on the collision course with the Earth, but we have 2 or 3 asteroids.
Scientists are racing to find a better solution. They have suggested attaching rocket engines to push the asteroid off course, or even solar sails to pull it into a different orbit. These are possibilities, but they sound like the stuff of science fiction. Researchers are putting their weight behind a more feasible solution: knock the asteroid off its collision course. The project's codename, Don Quixote. At the heart of the team is space mission analyst Chris Saunders from Kinetic Labs, England.
We're simply going to try and hit the asteroid and deflect it out of the way.
The theory is that a powerful strike delivered by a probe could knock the asteroid off its course, like a game of cosmic pool. Don Quixote is a 2-stage spacecraft made up of the impactor and the orbiter. The ion engine powers the orbiter to its target. Solar panels create an electric field which ionizes an ultralight fuel load of xenon gas, ejecting ions from the engine to thrust the craft towards the asteroid at up to 200,000 miles per hour. The aim is to catch the asteroid as far away from Earth as possible, so that even a tiny push will move it off course. The observer locks into orbit around the asteroid and guides the impactor to an inch-accurate surgical strike.
It would move the asteroid's orbit by maybe 50 to 100 meters. That would be enough for the asteroid to safely drift past the Earth.
If astronomers locate an incoming asteroid early enough, Don Quixote might be able to deflect it. But it's untested technology with a huge margin of error. Most scientists agree a backup plan is essential. To defend Earth from an asteroid strike, scientists have an ingenious and radical approach. Use an intense ray of light to vaporize part of the asteroid's surface, creating a jet of gas that will move it off course. It's a good theory, but right now the only place Massimiliano Vasile can test it is in the lab. He uses the Industrial Laser Lab at Glasgow University to gauge how much light energy it takes to move an asteroid.
We can see the effect of the light of the laser that basically was burning the rock. This is what we expect would happen in space when we focus the light of the sun on the surface of the asteroid. The fact that I obtain is exactly as if I had a rocket engine attached to the asteroid, but the difference is that the engine is the asteroid itself. This is in fact one of the most effective ways of deflecting the asteroid.
But shifting a full-scale asteroid would take a lot more light than an industrial laser. Luckily in space, we have a huge power source available, the sun. Vasile proposes using mirrors to focus sunlight on the asteroid, enough to vaporize its surface, just like the laser. But moving a 1,000-foot asteroid requires a mirror so large that no rocket is big enough to carry it into space. The solution? Use several small ones at once.
We propose to have a swarm of satellites, each one carrying a smaller mirror.
The mirrors would be around 60 feet across and precisely shaped to concentrate the solar energy, creating that vital jet of vaporized rock. Whatever system scientists end up using, the key is to catch the asteroid as early as possible. Astronaut Rusty Schweikert thinks it's vital to be prepared.
Even you and I driving our car, you and I typically have one chance in 10,000 that we're going to have an accident tomorrow if we're driving tomorrow. And because of that, we buy insurance. We're driving around the solar system on our planet totally uninsured. Why?
Someday, humanity will likely face another asteroid, like the one that exploded over Tunguska, or wiped out the Clovis culture. An asteroid just 150 feet across could kill tens of thousands of people, and we still don't know enough about them. The dangers and our lack of knowledge became all too apparent in September 2007. Carancas, Peru. Local people noticed strange lights in the sky, followed by a huge explosion. Villagers stumble on a 50-foot wide crater in the highlands. Locals claim it is caused by an asteroid, but not all scientists are convinced. Impact specialist Peter Schultz thinks it's a hoax.
My immediate reaction was, are you kidding me? This has really happened? It can't really be something that actually got through the atmosphere. This is science fiction. And the first pictures that came out, it looked like a B movie with this crater where Superman was going to walk out.
Schultz is disturbed by the size of the crater. It's tiny. An asteroid that small should never have made it through the Earth's atmosphere. It should have burnt up on entry. September 2007, a fireball blazes through the skies of the Peruvian highlands. It crashes to Earth near the village of Carancas in southern Peru, leaving a crater 50 feet in diameter. Eyewitnesses are mystified. At first, they think they're under attack.
We looked up at the sky and saw a smoky trail. First we thought it was a military plane. Then we saw that the object was approaching the ground, heading south. The workers said to me, "I think that plane is out of control."
una estela, ¿no? Cuando pasan por el cielo.
We were really scared. Even animals are running away due to the loud noise.
One explanation is an asteroid strike. But how did an asteroid so small survive entry into the atmosphere? It should have disintegrated before impact. Peter Schultz, one of the world's leading impact specialists, travels to the site to investigate.
I heard the stories in the media, I saw the pictures, and I thought, oh my gosh, I've got to go there.
The impact has blasted chunks of Earth into the air, damaging a building 150 feet away.
Wow. Oh, jeez. Oh. Oh, my gosh. Wow.
Whatever caused this crater was powerful enough to blast 100 tons of soil across the landscape.
This is clearly the pre-existing soil. Everything was just simply turned upside down over this.
This has all the hallmarks of an asteroid crater, but Schultz is skeptical. He needs to find a fragment to prove it. He exploits a common characteristic of this kind of asteroid, its magnetism. The metallic fragment and the shape of the crater convinced Schultz that this was an asteroid strike. But how big was this asteroid? Eyewitnesses tell Schultz the angle of impact. Now if he can discover the speed, he should be able to discover the size. At the NASA Ames Research Center, Schultz examines the fragment of asteroid under a powerful microscope. It reveals the true story behind the impact.
The fragments were deformed. There were fractures, and they were in a pattern that happens at around 3 to 4 miles per second, almost 5 times the speed of a bullet.
Schultz now has all the clues he needs to figure out the size of the asteroid.
From those pieces of information, the angle and the speed, we can determine how big it was. And it's probably somewhere between 3 feet and 6 feet.
It's an extraordinary discovery. Up until this moment, scientists believed rocky asteroids this small burned up before they hit the ground.
Here we have a puny thing, only about 3 to 6 feet across, that somehow made it to the surface. This shouldn't have happened. This just shouldn't have gotten through the atmosphere. In this case, it made it through. It not only made it through, but it hit hard.
How it got through exactly is still a mystery, but the fact that it did is alarming. If a tiny asteroid like the one that hit Caracas strikes a crowded city, it could potentially kill dozens, if not hundreds of people.
Will it kill people? Yeah. The clock is ticking. It's coming.
This is not one of those giant things. This is the type of thing that if it happened in New York, it would have caused some serious damage. It probably would have gone right through the ceiling of a tall building and gone through about 4 or 5 floors before it rested.
In Peru, we were thrown a hypervelocity curveball.
Rusty Schweikert believes that now is the time to take the threat from smaller asteroids seriously.
A hurricane, we can't prevent. A flood, we can maybe do some things to prevent. We can certainly mitigate against these things. But preventing is an unusual opportunity in a natural disaster. We can prevent this from happening. If we do our work with near-Earth objects, we can prevent asteroid impacts from ever happening.
There is little doubt that an asteroid will someday threaten the Earth. The question is, will we be prepared to deal with it in the not-too-distant future?